All right, we'll get started here in just a couple minutes. Give a few minutes for stragglers. How many of you read chapter 8? Questions on chapter 8, anybody? Go ahead.
The altimeters.
Okay.
It states that the flying from high to low pressure without adjusting the altimeters. How often do you have to adjust the altimeter?
Okay, we're gonna.
Before flight?
That's definitely something we're gonna definitely cover that. Yep. Any other questions?
Sorry, I got some.
Yeah, you got more? Go ahead. Yeah.
The trend vectors.
The what's that?
Trend vectors.
Trend vectors.
Just need a good explanation.
Yep.
On that. Give them a gentle line.
Yep. Trend vectors. Okay.
In a skid or slip turn,
Okay.
do your eyes actually look at the gauges rather than the field?
Uh-huh. That's a great question. How to know?
So I know you're supposed to be paying attention to other things you're running into,
Yep.
birds, planes, whatnot.
Yep. When you get good at it, and if you're taught correctly, you never have to look at the ball. You'll feel it. I'll tell you how. Tell you how to do it. Any other questions? Go ahead.
You're flying from here to South Padre.
Okay.
And it's looking for a heading. Where do you find those numbers? Because it's asking for in degrees.
Okay. So we're not going to really be talking about that. Well, we kind of will. We're going to talk more about that when we get to the cross-country flight planning.
Okay.
But the discussion today, especially when we get to the directional gyro and the magnetic compass, you'll understand. That'll become much more clear to you.
Not on the plane, but on the map itself.
I understand. Yep. I understand. Yep. How you get it on the map, that'll come in the cross-country flight planning.
Okay.
Yeah. Okay. So yeah, that'll come in cross-country flight planning.
Last one.
Okay. Go ahead.
Certification of aircraft regulations cannot be used for ops when ownership is transferred.
Say that again.
Certification of aircraft regulations cannot be used for operations when ownership is transferred. So if you sell me your plane,
No, you can use right away. I'm not sure of the. You get a temporary. So if I were to sell you one of my airplanes, you have I think 90 days to do something with it, but I give you a document that you carry with you. That is your proof of ownership now. Yeah.
just like on a vehicle.
Just like on a vehicle. Yeah. No, you can absolutely use it you can fly it away right away. Yep. Yep. Any others? These are good. No more? Okay. All right, see what he did? This is what I want all of you to do. When you read, I want you to come with these questions. Whatever you're reading, whatever doesn't make sense, come with the questions. I'll write them up that way. I make sure I cover them all. With these that he asked, I would definitely cover this trend vector, though I wouldn't necessarily perhaps cover it if you hadn't asked me about it now. So I'll cover it now. I'll make sure I cover that. All right, we'll give it one more minute. I see another car coming in there. We'll get started. How many of you are already flight training? I know just one you are. Did I have you do one of these, just one? Okay, this is for the tower. They want feedback. Be honest. Don't put your name on it, and be brutally honest. Anybody else? Flight training already? You already did yours? Yeah. Every year or so, they want to know how they're doing. So just you can give it back to me, or you can give it to the desk when you're done.
Really, all we're doing is making sure nobody's dead. That's the whole purpose. That's why it's because we are an unpredictable aircraft. Usually, you get in there, you go straight up, or go wherever you want to go. All right, now let's step 2.
We are full. All right, so for anybody that did not sign in, if you didn't, if the sign-in sheet's there, just at the break, you don't have to get up and do it now, but just sign in at some point today. Make sure you get your information on there. Okay, let's get started. We're going to talk about flight instruments primarily, and then at the end, or the last half hour or so, we're going to talk about documents, aircraft documents. Okay, can you see okay from over there? Yeah. There's seat right here, and over here there's a couple seats. One right here. There you go. Okay, how many of this is your first class? Raise your hand if it's your first class. Just okay, good. Then I'm good. I'm glad you're right in the middle. You can see real good. What's your name? Max. Max. Nice to meet you, Max. I'm David, and this is the rest of the class. Okay, flight instruments. We're going to talk about. So when we talk about flight instruments, you know, you might get this picture of a cockpit of an airplane. And you have all these gauges and dials, if they're round gauges or a flat screen, with lots of stuff on it. Okay. There's a lot of stuff that you might see in the instrument panel, but all we're going to talk about are 6 of these instruments, and they're called the flight instruments. Sometimes in the old, we kind of lovingly refer to these as steam gauges, right? But that's the 6-pack, okay? So we call that the 6-pack, and these are the flight instruments. And by flight instruments, what we're saying is by properly interpreting and reading those instruments, we can, without looking outside, not that we're not going to be looking outside because we're training VFR right now, right? So we are looking outside. But if you weren't looking outside, by looking at those 6 instruments, you can determine the aircraft's flight attitude. You know, whether you're climbing, descending, turning, you know what the attitude is and what the condition of the airplane's, what its flight condition is. So those are flight instruments. They're not giving you anything. They're not telling you anything about the weather. They're not telling you anything about the engine condition. Not telling you anything about anything but the flight conditions of the aircraft. So here recently, within the last dozen or so years, maybe a little longer, 20 years or so, these electronic displays have started to crop up, and this is pretty much what you see now in newer aircraft. Newer aircraft are going to have something like this.
Is that what's in your plane?
That's what we have in our plane. Not this display, but they're flat screen. We don't have a 6-pack, no. But the chances of there's still a lot of airplanes out there that have 6-packs, so you need to understand how these, and primarily what we're talking about today is how these operate. The operating function and the error modes, failure modes on these types of instruments right here. Okay, there are two classes, if you will, or 2 types of instruments here. One is pitot-static, 3 of them are pitot-static, and 3 of them are gyroscopic. The pitot-static and the gyroscopic also apply over here, and I'll show you what's what. In fact, I'll kind of show you right now. Let's go through the 6. You have the airspeed indicator right here, okay? Here you have the airspeed indicator over here, and what you're going to notice that they're kind of laid out, kind of sort of in the same way, not exactly, but kind of. Airspeed indicator, attitude indicator, so this is giving us pitch and roll information right in the middle. Attitude indicator right in the middle. Altimeter. So across the top, you have them in that same order. And no matter what kind of all the glass screens I've seen, they all have up here that laid out pretty much just like that. So it follows this same format right here, okay? Now when you get down here on the bottom, this might be a little bit different. In fact, this usually is a little bit different. In the middle bottom, you have your heading indicator, okay? And again, most flat screens will have the heading indicator, or you could have it set up where the heading indicator is right just below, just like this. So these top 3 and this middle one are pretty much always set up like this. These 2 can be in different places, okay? This is our turn coordinator, and this is our vertical speed indicator. On this display, the vertical speed indicator, and on most flat screens, the vertical speed indicator, which is another altitude indicator, if you will. It's not telling us our altitude, but it's telling us how rapidly we are changing altitude. Okay, so it has to do with altitude. So it's telling us how fast are we going up or down in feet per minute. And so it's kind of related to altitude, altimeter. And so it's over here on the side of the altimeter right here. So the vertical speed indicator is over there on the side. And you'll see that in our planes that way and most other flat screens the same way. And then the turn coordinator you've got two things here. You've got a turn coordinator, which is this little airplane, and you've got a slip skid indicator, which is the ball. So the turn coordinator is typically, the slip skid indicator here is this little bar right here, and the turn coordinator,
Where the 270 is in the center?
yeah, right here. There it is right there. Turn coordinator is right there. So you can set, and this is different depending on the airplane you're looking at, depending on the screen that you're dealing with, okay? But the turn coordinator, we'll talk about what it is, but it's basically giving you turn rate. It's telling you how many degrees per second you're turning in standard rate turns, okay? All right, so that's our 6-pack. We have 6 instruments. We have airspeed indicator, attitude indicator, altimeter, turn coordinator and slip skid indicator, heading indicator, and vertical speed indicator, okay? That's the 6-pack. That's the 6 flight instruments. When you guys move on to start working on your instrument rating, then that is basically 40 hours of just staring at these without looking outside, staring at those flight instruments and learning how to control the aircraft under instrument conditions or without looking outside the airplane, okay? All right, so we're going to break these instruments down into two sets, pedostatic and gyroscopic. Those are the 2 types of instruments we have, pedostatic and gyroscopic. So let's first talk about the pedostatic instruments, which happen to be the airspeed indicator, that's a pedostatic instrument. The altimeter is a pedostatic instrument, and the vertical speed indicator. So these are the pedostatic instruments. So here, here, and here. These are pedostatic instruments. Okay, the other 3 are gyroscopic instruments. All right, we're going to talk about pedostatic first, and this is a kind of a layout, a schematic, if you will, of a pedostatic system. Regardless of whether you have a 6-pack or whether you have a flat screen electronic type setup, you still have a pedostatic instrument, a pedostatic system. It's just that the pedostatic system is connected to an air data computer, which then feeds information to the screen, as opposed to going into each individual instrument like this. You still have all the plumbing behind the scenes in the airplane. All the plumbing is there, but rather than the plumbing going to a vertical speed indicator and an airspeed indicator and an altimeter, these individual instruments, it goes to a box, a computer, basically, and then that computer sends information to the screen, okay? An air data computer. So let's talk about the parts of this, or the pieces in this system. It's called a pedostatic system, and we have a pedo tube, and we have a static port. So that's the pedostatic system. Everyone has seen the pedo tube on our airplanes, right? Where's the pedo tube at? Sticking out the wing. And that's usually where you see them. You usually see them sticking out the front of the wing. The pedo tube is responsible for getting that ram air pressure. So when we're flying, that ram air pressure is being pushed right into that pedo tube. Okay? So the pedo tube takes that ram air pressure. The static port, everybody know where the static ports are on our airplanes? On both sides, we have 2 of them. We have one on each side, just in front of the doors, entry doors. One on both sides is a little tiny hole. Those are static ports. And what the static port is measuring is the static pressure. So the pressure of the air that's not moving, rather than the dynamic, rather than the ram air pressure coming in here, it's measuring the static pressure. So a couple of days ago, or on week 1, for those of you that were here on week 1, I drew a little 1-inch square. And I said that there's a certain amount of pressure being exerted against that square on a standard day at sea level. How much pressure was that in inches of mercury? 14.7 pounds per square inch, but in inches of mercury, how much was it? 29.92 inches of mercury. Okay, so if the airplane, in this case, if you have an airplane sitting at sea level on a standard day, then the amount of pressure the static port is feeling is how much? 29.92 inches of mercury. Okay, so this little port right here is measuring how much pressure is being exerted right there at that hole. Okay, so as we climb up in the atmosphere, what's going to happen to the pressure being exerted at that little hole right there? It's going to decrease. Right, it decrease. Okay. So the static port is simply measuring what's the pressure being exerted on me right now, at this point right now, up in the atmosphere. The pitot tube is measuring how fast, how rapidly are those molecules of air going in there. That's what the pitot tube is doing. So it's measuring ram air pressure. I got that? That's a pitot-static system. Okay. So we plumb the pitot tube and the static port to the pitot-static instruments. But they don't all get plumbed, as you can see in the diagram, they don't all get plumbed to every single instrument. You notice that? All of them have a static pressure plumbing. All three instruments get static pressure information. But only one of them gets ram air pressure. The airspeed indicator. The airspeed indicator gets ram air pressure. And if you think about it, that would make some sense, right? I mean, that's the one that's measuring how fast we're moving, right? How fast those molecules are hitting the pitot tube and going into the pitot tube. So the airspeed indicator gets both ram air pressure and static pressure, and essentially just turns that, and so all this really is, you can think of it, I can tell you what you think about an airspeed indicator as. It's nothing more than a pressure meter. It's measuring pressure. Okay, and in what it's measuring, you have static pressure coming in here, you have ram air pressure coming in here, and it is measuring the dynamic pressure. So this is a dynamic pressure meter is what that is. Okay, so it's taking the ram air, how fast are the molecules coming in, and then it's working that against what's the static air pressure, and it's turning that into a dynamic, an overall dynamic pressure, and then reading that out in some airspeed. Might be miles per hour, knots per hour, kilometers per hour, whatever. However you want to paint the numbers on the dial. Okay? Does that make some sense to you? Okay, static pressure and ram air pressure, those two combined are the dynamic pressure. Now I'm going to say something right now that is really important in aviation. Everything about flying an airplane is about dynamic pressure. Everything. The wing stays in the air because you give it enough dynamic pressure. Everything. Okay. Look at that formula up there. You see the two components within the parentheses, 1/2 rho and velocity squared? That is dynamic pressure. The 1/2 rho is this. The velocity squared is that. So in the lift formula, what I put in parentheses is the dynamic pressure. Okay? So this instrument is giving you the density times the velocity. Giving you the density of the air times the velocity that we're moving through the air. Okay. The vertical speed indicator is simply telling it doesn't need to know how fast the molecules are coming in. All it needs to know is, where am I at in the atmosphere? What's the density of the air in the atmosphere, right? Well, let's go to the altimeter first, so it'll be easier to understand. If we're at sea level in this airplane on a standard day, and our altimeter, we're reading 0. This our altimeter is broke. This one's reading 10,000 feet right now because that little hand's over at 10,000 feet. But let's pretend it's reading 0, okay? And it read 0 at the same time, and I'll get to this a little bit more, that we have it set in the little Colesman window to 29.92. So we set it to 29.92, which is what the pressure should be at sea level, and it reads 0. And then we take off and we climb. When we get to 1,000 feet, or as we're climbing, these hands start, showing us altitude gain, and at 1,000 feet, it'll show us 1,000 feet, and so forth, and so on. So all it's measuring is what is the pressure of the air. It's measuring the static pressure. And the static pressure is approximately 1 inch lower at 1,000 feet, which turns the hand 1,000 feet. Go up another 1,000 feet, it turns it another 1,000 feet, and so forth. So all it needs is static pressure. It doesn't care how rapidly we're moving through the air, it cares where we are in the atmosphere statically. What's the static pressure? The vertical speed indicator is the same kind of thing, except it's not telling me we're at 1,000 feet or 5,000 feet. It's saying how rapidly I'm changing altitude. Now, we'll get into the guts of it here in a minute. I'll explain that to you. But from the standpoint of what it's reading, that's what it's telling me. This one's telling me, hey, I'm at 1,000 feet, and maybe I'm climbing. The needle's moving up, or the needle's moving down. This one tells me how many feet per minute it's moving up or down. Okay. That's the pedostatic system. So it's a pressure, it's an air pressure, it needs air pressure, it needs atmospheric conditions in order to read what it's giving us. Okay? Any questions so far on that? All right. All right, let's look at the altimeter more specifically. Yes?
You said earlier, so like whenever, like a normal day, whenever we're on the ground with the static floor, it's measuring down 2992. And it's like going into it. As we go up, that decreases. Correct?
Yes.
Okay.
The pressure decreases. Yep. All right, so let's look at the altimeters specifically. So the altimeter is measuring the height of the aircraft above a given pressure level. Okay, so what you want to understand with an altimeter is, think of an altimeter like a tape measure. If I take a tape measure, if I want to know how tall I am, I get shorter the older I get, but if I'm wearing tennis shoes, I'm 6 feet tall. So if I take a tape measure and I want to know how tall I am, I have to start that measurement from someplace. I need some level to start the measurement, right? In this case I'm talking about now, I'm going to start at the floor. So I'm going to set my tape measure to the floor and then measure up from wherever I'm standing. And I know my altitude at the top of my head, which is 6 feet. An altimeter is doing the same thing. But what it's doing is it's measuring the height above a pressure level. A pressure level. So what is the standard pressure level, or what is the pressure reading at sea level on a standard day? 29.92. So if it's a standard day out, if the altimeter, you get ATIS, you get, AWAS ATIS, and you get an altimeter setting, and it tells you the pressure, the setting is 29.92. What they're saying is at sea level, the pressure is 29.92. So what I'm going to do then is I'm going to set my tape measure to 29.92 and measure up and say, okay, where am I at from 29.92? If you listen to ATIS and it says the pressure, like these last couple days, it's been, how many of you have flown this past week? The pressure's been like 30.6, like really high pressure. So what they're saying is the pressure at sea level today. So in other words, well, somebody get the pressure, somebody get ATIS for me right now while I'm talking. Now we'll use today's numbers. If it were 30.6, what they're saying is that, hey, if we dig a hole, what's the field elevation of this airport? Who knows? 658, so about 650 feet. So what they're saying is if we dug a hole 650 feet down and we dropped a barometer in there, it would read 30.6. So way down there at sea level, it's 30.6 inches of mercury. So I'm taking my altimeter and I'm dropping the end of it down to 30.6 and I'm reading, 658 feet.
So basically high tide.
Height above sea level, yeah. What is it? Who's got it?
3059.
So, boy, right on it. Right on it. Okay, so it's very high pressure, right? Because standard pressure is 29.92. But the pressure at sea level today is 30, we'll just call it 30.6 to make it easy, is 30.6. So that's way, much higher. So it's as if, really, if you think about it, it's as if we're lower. It's as if sea level got lower because now we have more altitude above us causing more weight. It's a higher pressure down there, if you think about it that way. So that's all an altimeter is doing. You're saying, take my tape measure and send it down to where the pressure is this. Stop it when the pressure reaches that, and now let me read how high I am above that pressure level. That's all an altimeter is doing. Okay? And how we send that little tape measure down there to get to that pressure level is through this little Colesman window right here. This little, and we have the flat screen, and on the other side we have one of these. And you should be setting both. and right in there, and I'll pass this around, you turn that little knob and you set the pressure level right there. Whatever it is, so whatever altitude, whatever, if the ATIS says 30.59, you set this to 30, way up there, 30.59, right about there. I'll leave it right there and I'll pass it around. Just pass it that way. You set it right.
Set that every time before you start to fly.
Every time. And not only that, because you asked this question, altimeter, how often, you asked it here, how often do you set it? Frequently, while you're flying. Even while you're flying, okay? Because the pressure here, somebody look up the altimeter setting at San Marcos. It might be close to the same, but it probably won't be exact.
3061.
3061. The altimeter setting's 20 feet different. It's different by 20 feet. It's off by 20 feet, right? So the pressure changes over short distances. So as you're flying, I think you said, what if I'm flying to, I forget where you said? South Padre. You're flying to South Padre. What you're going to do while you're flying along is you're going to be listening to other airports and other reporting stations. You're going to be listening for that altimeter setting, and as you fly, you're changing your altimeter. You're adjusting your altimeter. You're adjusting your altimeter. Because if you don't, if you fly from high pressure to low pressure, high to low, you're flying downhill. If you're not resetting your altimeter, you're flying downhill. I'll show you that in a little more detail. You'll hit the ground, yeah, if you're not paying attention, yeah. Okay, so altimeters work off of pressure levels. That's the key thing there.
Dave, is there a time where you don't want to switch it?
No, never. There's never a time I can think of when I don't want to keep my altimeter set to the current altimeter setting.
Got it. How do you adjust it on the flat screen system?
Have you started your flight training yet?
No.
Okay, it's real simple. Well, I'll show you right here. You can stay there, just duck. Right here, this knob, that sets the altimeter, and you're setting that number right there. And when you set the actual altimeter, there's your actual altimeter over there. This is your mechanical altimeter, and then this is your electronic, and you set it with that knob right there. In most of the planes, in 406, this little panel is down here. Okay,
Yeah,
but there's
I think that knob says something like dynamic something too, that it indicates what you're messing around with.
Yeah, it's just underneath it. So as you're turning that knob, you see the pressure setting right here. Yeah, you see it right there. You can also get to it through the screen, through the buttons on the bottom of the screen. And most of these flat screen displays, not most, all of them, if they have a separate control knob system to make it easier to change settings, you can always change settings from with the screen itself with the buttons. There's always a way to do it that way too. Okay, so let's look at the altimeter and its principles of operation. We only have a static port. As you can see, where's the altimeter at that's getting passed around? I'll turn it around to the back side. There's only one port on the back. See that? There's only one plumbing hose that plugs into it. And that hose is comes from the static port. Whereas if you look at an airspeed indicator, you got two ports, because you need static and you need ram air. You need both ports. You need both plumbing hoses going into the back of an airspeed indicator. But the back of that guy, you only need one. So that's right here, it's a static port. So what you have is a sealed case, so that case is sealed. You have the static air pressure going into this case. So the pressure inside this case is going to be constantly changing, right? As you descend, there's higher pressure. As you ascend, there's less pressure. The air thins out. The air thins out. As you go up, the air thickens. The density of the air thickens as you descend, all right? You have we call an aneroid wafers, but these are basically little wafers that have an internal pressure to them, okay? And as the pressure inside the case increases, those wafers squeeze. As the pressure inside the case decreases, those wafers expand. And so as those wafers squeeze and expand, it turns little gearing mechanisms and turns the dials on the altimeter. That's how the altimeter works. So when you set it with the Colesman window, you're setting it for a sea level pressure, and then as you go up and down from there, that little aneroid wafer squeezes and opens and closes based on the pressure inside this case. Is that logical? Okay. All right, now we'll look at these effects of non-standard pressure and temperature. This is what we were talking about, the reason that you want to set your altimeter as you fly, because non-standard pressure and temperature will affect that, okay? All right, so here's this is temperature. So we say, there's a saying, we say high to low, look out below, or hot to cold, look out below. Both have the same effect. This is showing hot to cold. So if we're flying from a temperature of 30 degrees Celsius to a temperature of 0 degrees Celsius, if we were, and remember, there's a pressure, the altimeter is reading pressure levels. So if we started over here and we had, let's say we took off from this airport, and at that airport, the altimeter setting was 30.00, let's say, whatever it was. And we take off and we climb to 5,000 feet and we start flying, but we never touch our altimeter again. We don't reset it. We have it set to 30.00. As the temperature decreases, the pressure setting would change, and if we don't change it in our altimeter and we simply turn on the autopilot and tell it to hold 5,000 feet, here's what it's doing. It's holding 5,000 foot pressure level. It has no idea how high we are above the ground. It's just, it knows how high we are above the pressure of 30.00, which over here is this level, is this height, and over here is this height. So understand, when you're looking at your altimeter, is it telling you how high you are above sea level? It's supposed to be, but that depends on whether you have it set properly. It has, there's no radar. It's not a radar altimeter. It's not bouncing a signal off the ground to tell us how high we are above the ground. It's based on you properly setting the sea level pressure for the area that you're flying in. If you don't have it properly set, your altimeter isn't reading properly. So you have to reset it as you fly, as you fly, as you fly. You're listening to altimeter settings at different airports as you go. And you don't have to be flying right over the top of one. If there's one 20 miles over there, listen to it. Set it to whatever that is. Is it going to be exactly right? No, but it's going to be pretty close. But if you're flying through here and you listen to San Marcos and you set 30.61 and it should be 30.59, you're only 20 feet off, right? But get it as close as you can. All right, so that's high to low, look out below. That's what you want to think about. High to low, look out below. Hot to cold, look out below. All right. And the key thing here, is, if you remember, is it's reading pressure levels. It's just a pressure. You're dropping your tape measure to a level of pressure, not to some solid thing. Okay? All right. Oh, this is obvious now based on what we've talked about. 2 ways to make it change. Turn the little knob or climb and descend. That'll cause it to change. That's pretty Captain Obvious there, right? All right. Let's talk about the different types of altitude. This is when you start flying, it'd be nice to say what's your altitude and it means one thing. That'd be nice to say, right? But altitude can be a lot of different things, all right? So let's talk about the different types of altitude. So we already said altitude is the vertical distance above some point or level used as a, so we got to have some reference, right? So let's talk about, come on. There we go. All right, so the first thing we'll talk about is indicated altitude. Indicated altitude. Indicated altitude is very simply what you read. What is the instrument indicating? What are you looking at? What's the number? So the indicated altitude could be a lot of different things. It depends on what you have it set to, right? But the indicated altitude is what you read. That's what's read on the altimeter. Okay, the next type of altitude is true altitude. True altitude is your true height above sea level. So when we say true altitude, we're saying this is how high we are. We truly are this high above sea level. That's true altitude. This is the altitude that you're going to be working with while flying below 18,000 foot. But if you're flying below 18,000 feet, this is the altitude that we want to be, this is what we want our indicated altitude to be reading. When we're flying below 18,000 feet, 99% of the time, we want what we see, what's indicated, to represent true. How do we do that? We keep the Colesman window set to the sea level pressure. If the Colesman window is set to sea level pressure, then our indicated altitude is reading true altitude. Okay? That's true altitude. Next type of altitude is absolute altitude. Absolute altitude is height above the ground. So where I'm standing right here, my true altitude is, let's call it 650 feet. My absolute altitude is 0. Okay? That's absolute altitude. Pressure altitude. You're going to hear pressure altitude a lot as we go forward into the training here, as we go forward into the classes here. Pressure altitude is the aircraft's, or the instruments, because the instrument is in the aircraft, okay. It is your height above the standard datum plane, the SDP. So get that in your head. This is a big one. Pressure altitude is height above the standard datum plane. Okay, the standard datum plane is wherever 29.92 exists in the atmosphere. Don't hear what I didn't say. I did not say the standard datum plane is sea level. I said the standard datum plane is wherever 29.92 exists in the atmosphere. If it's a standard day, then the standard datum plane exists at sea level. How often is it a standard day?
Almost never.
Almost never, right? Sometimes the pressure is 29.92 at sea level, but even that's not, even that, that happens frequently, but it's not every day. Okay, so the standard datum plane is not sea level unless it's a standard day. Standard datum plane today, as an example, is where? Let's diagram it here. Let's just diagram it. Oh, let me close this all the way so you can see here. All right, so let's say that this is sea level right now. Right here is sea level. That's sea level. What's the pressure right now? We'll call it 30.6 because that's easy. 30.6. Okay, that's sea level. Where's the standard datum plane from this?
Be below or higher.
It'd be above it. It'd be up here. So the standard datum plane is up here. By how far? Well, 30.6 minus 29.92 is what? I'm not doing the math. 58? 0.58 times 1,000 is what? 580 feet. So the standard datum plane is only 70 feet below us right now. That's how high the pressure is right now. So here's our airport sitting right up here at 650 feet. This is at 580 feet. And sea level is way the heck down here. So today, right now, the standard datum plane is right below us. It's not at sea level, it's way down below us. Okay? So right now, our pressure altitude would be what? About 70 feet. Pressure altitude's about 70 feet right now. Not 650 feet, 70 feet, because the datum plane, the SDP, the standard datum plane, which is wherever This exists in the standard datum plane is wherever that is. That's the standard datum plane. Pressure altitude says, how high am I above that? So today, the pressure altitude right now is approximately 70 feet. Does that make sense? Okay, so that's pressure altitude. How high are we above the standard datum plane? So if I want my indicated altitude, if I want what my instrument reads to read pressure altitude, what do I have to do? Crank it to what?
70.
Well, I want it to read 70. I want it to read what the pressure altitude is. How do I do that? What do I set it at? I set it to 2992. What I do is I take my altimeter and say, I want to send my altimeter down to 2992 and read how high I am above it. When I do that, I'm reading pressure altitude. Okay, that's how we get pressure altitude. There's two ways to get it. The easiest way, if you're near an altimeter or you're near your airplane, is to simply go to your airplane and put 2992 in it and read it. And that's you're reading pressure altitude. The other way you can do it is mathematically, because we know that pressure changes how much per 1,000 feet? 1 inch per 1,000 feet. So we could then say, let's do this. Let's see if we can come up with 70 here. We'll use the exact 30.59 though. So what we do in this case is we say 29.92 minus 30.59 is what? Again, I do not do math in my head up in front of a bunch of people because I always get it wrong. So somebody do it in a calculator for me. I don't know. Is that right? I thought we came about 50. It was near 58 or something. 0.67. Okay. 0.67. Is it negative 0.67? Yes. Okay. So we did this. So the 58 was wrong a while ago. Somehow we came up with that. 0.67 times 1,000 equals what? 670 feet. So pressure altitude is actually above us by 18 feet or something like that. So it's above us. The standard datum plane's up here somewhere. Does that make sense? How that works? Okay. So there's two ways to get pressure altitude. You can do that formula, which is real simple. Take the standard pressure minus the altimeter setting, multiply that times 1,000, and then adjust, and then you'd add back your altitude. Okay? Or you could just go to your altimeter and set it. All right, that's pressure altitude. The next altitude is density altitude. Got all these altitude. See what I mean? It would be nice to start learning how to fly and just look at an altimeter and say, well, that's our altitude. Well, what kind of altitude are we looking at here? We've got a lot of different altitudes we have to deal with. Okay, density altitude is pressure altitude adjusted or corrected for non-standard temperature and pressure, or non-standard temperature and pressure, because you have to adjust pressure altitude. So this is the altitude, and I call this, when we get into the performance class, we haven't done performance yet, have we? No. When we get into the performance class, I call this the holy grail of altitudes. So as it pertains to performance and how the airplane performs, how much runway do I need? What's its climb rate going to be? How fast am I going to cruise? How much runway do I need to land? All that kind of stuff. The performance numbers, all about this right here. And what this is telling us is how thick or thin is the air? What's the density of the air? It's the density altitude against standard altitude. So an example would be, let's go back to the standard day. Let's think about the standard day. Everybody got a picture of the standard day? What's the pressure at sea level on the standard day? Okay, what's the temperature?
59.
What is it in Celsius? Because it's easy. 15 Celsius. It's easier to work with Celsius. What's the lapse rate? How much does it change as we go up? 1 inch of pressure? 2 degrees Celsius. All right. Therefore, if we go to 10,000 feet on a standard day and everything lapses properly, okay, everything lapses properly, what is the pressure? And I took a barometer up there. What would it read at 10,000 feet? Approximately. because it drops approximately 1 inch. What would it be approximately at 10,000 feet?
19.
19.92. And what would the temperature be up there? -5. Going to drop 20 degrees. So we go from -15, drop 20, we go to -5. I mean, we go from 15, drop 20, we go to -5. So on a standard day, when I get to 10,000 feet, the temperature, if it's standard day, should be -5 degrees, and the pressure, if I take a barometer up there, should read approximately 20 inches, 19.92 inches, right? How often does that happen? Never. So the density altitude on a standard day up there would be 10,000 feet, but it's usually never a standard day. So the density altitude tells me what would it be? What is it up here on this day? Okay. So let's say you're at an altitude of a true altitude of 5,000 feet. You're up on a mountain somewhere. You're at 5,000 feet. That's the field elevation of this airport. And the temperature and pressure are such that the density altitude is at 10,000 feet. Okay? What that means is that the density, you're physically standing 5,000 feet. You're truly 5,000 feet above sea level. You're at zero absolute altitude, but you're at 5,000 true altitude. Okay? But the density of the air is as though it's a standard day at 10,000 feet. It's thinner. Everybody with me? No? Not with me? Okay. Thank you for being honest. Let's look at just density for a second here. Let's say down here at sea level, let's say here's sea level, let's say these are air molecules. That's the density of the air molecules at sea level. We'll go up to 10,000 feet, and here's the density of the air molecules at 10,000 feet. Okay? You're at 5,000 feet. On a standard day, the density at 5,000 feet should look like that, something like that, okay? All right. So on a standard day, this is a standard day, that's what we would have, okay? But you're not on a standard day. You're at this 5,000 foot airport, and on this day, the density is like this. The density resembles that. You are at a 10,000 foot density altitude. Even though you're truly at 5,000 feet, the density is as if it were 10,000 feet on a standard day.
And that's because of the difference in
Pressure and temperature. Pressure and temperature, okay? High temperature and lower pressure, or some combination of that, would cause a high density altitude. In that scenario, your airplane's performance is going to do that. Yeah. So we're here, let's say you take off and you need this much runway to take off. Up here, you need that much runway to take off. Well, when you get here, you're going to need that much runway to take off because the air got a lot thinner. So density altitude from a performance standpoint, that's why I call it the Holy Grail. You don't care about it from a performance. When you want to know how much runway you need, I don't care what altitude the airport's at. It makes no difference. What matters is the density altitude. What is the density of the air? If you're at Key West, which is at 0, that's at sea level, and it is, let's say, even if it's standard pressure, 2992, but if the temperature is 100 degrees, the density altitude's not 0. Density altitude's much higher. It might be 3,000 or 4,000 feet. So you're at Key West, where you think the density's like this, but the density's really like that. So what matters is density altitude from a performance standpoint.
So if it's opposite, like you were just saying. So this is basically like you're in Denver,
Yeah.
but now you're at Key West and it's hotter. So you're going to need less runway?
No, you need more. It's the same. So this would. So if this is, let's call this 4,000 feet, true altitude. you're at Key West, but it's as if you're up here at 4,000 feet because the density altitude is as if you were higher than sea level because the air is thinner because it's hotter.
Not necessarily colder.
Okay, so it is colder up there. So there's two things that affect the density of the air. This is where part of the confusion that a lot of people get into when it comes into performance. There's two things that affect density of the air. What are those two things? Pressure and temperature. Okay, pressure and temperature. Pressure is going to affect it. In this case, pressure is giving you a bigger negative effect than temperature is giving you a positive effect from a decrease in temperature standpoint. So you're going up 2,000 feet and maybe the temperature goes from 30 degrees Celsius to 25 degrees Celsius, okay, or something like that. But the fact that, well, actually in this case you're down here on the ground. So the fact that the fact that the temperature is so high, you're getting a giant decrease in pressure due to the temperature. I actually said that backwards a second ago. You're getting a giant decrease in pressure because of the temperature. Yeah, with heat.
Increase with cold.
Sure, because think about a hot air balloon. What happens to the air inside a hot air balloon when you put hot air in it? It expands. It gets less dense. Yeah. Okay. All right. All right, let's look at this to give you an example of high to low, hot to cold, look out below. Okay, so here we have sea level, 1,000 all the way up to 10, let's call it 9,000 feet. I can't really see the 10,000 up there. And you got ground here, you know, you got a sea, you got some water, sea level, you got a mountain or something. This pink line, I'm using that pink line to represent the standard datum plane. So this is the standard datum plane. Therefore, this is the standard pressure level. So what is the pressure along this line? 29.92. Okay. So if the pressure along this line is 29.92, let's say you are at an airport right here. You're at an airport located right there at sea level. And you listen to ATIS. What will ATIS say the pressure, what will ATIS tell you the altimeter setting is going to be?
27.92. No, it's the other way.
Other way.
31.
It'd be, now that'd be really, really high. This is quite exaggerated, but I'm trying to get the point across. It'd be what?
31.92.
It'd be 31.92. That would be the pressure right there in this example if the sea level, if standard datum plane is up here. If I came over here and there's an airport located right here, what would the pressure setting be right there? 29.92. I mean, it's basically, that's where 29.92 is intercepting sea level. Okay? If I had an airport over here, let's say I'm flying out of an airport which is located right here on the side of the hill there, what would the pressure level be right there? Well, let's see, these are 250 foot increments, so you got 3 of them there.
750 less.
Yeah. Well, maybe it'd be better to do it. Let's make it easy. I don't want you to have to do that much math. Let's go 1, 2, 3, 4. Let's go right here. So you happen to be flying along. Well, you got a mountain. You got an airport right there. Right there. What would the pressure level be here? 28.92. See how that? Can you see? Okay. Yeah, there's another at the break if you want. There's a chair back. There's another seat back over there. Does that make sense to you guys? Okay. So your altimeter setting, when you get an altimeter setting, it's always saying what is the pressure right here? What's the pressure along this line right here? It's not saying where is the pressure level, it's saying what is the pressure right here. Based on what the pressure is right here, you can calculate closely where the pressure level should be, or where the standard pressure level is at, because you know in the standard atmosphere the pressure changes approximately 1 inch per 1,000 feet. And so you can back into where 29.92 should be based on what they're saying it is at sea level. Is that understandable? This is why, you can go ahead and open that up. This is why it's important for us as pilots to know some of these basic things like the standard atmosphere. All right, so let me give you an example of high to low, look out below. We take off right here, the pressure setting is 2992, and we climb up to, let's say, 8,000 feet. And we want to go that way. And we want to clear that mountain, and we know 8,000 feet will clear that mountain. But we get up there and we turn on our autopilot, and then we just stop looking out the window, or it's night, and we turn on the autopilot. And that autopilot keeps us at 8,000 feet. And we never readjust the altimeter setting. Where are we going? Right here. Right into the side of the mountain, because we're still 8,000 feet above the pressure level. So our altimeter is still going to read 8,000 feet as we fly right into that mountain. Because as we're flying, we're not readjusting the pressure levels. If we did, then this is what would happen. Right? See what I'm saying?
They don't have an actual autopilot. You have to constantly.
Autopilot is just maintaining altitude that the altimeter says to maintain. So you have to adjust the altimeter to keep the autopilot flying correctly. Yeah, you can't fall asleep in the cockpit. You can't do that. Okay, does that, see how that works a little bit? Okay. So all your altimeter is doing is following a pressure level, or is reading height above a pressure level. Okay. Let's look at the vertical speed indicator. Vertical speed indicator is similar to an altimeter in its operation, but rather than giving us an altitude, it's giving us a rate of change in feet per minute. What's the rate of feet per minute of climb, or the rate of feet per minute of descent? That's what it's giving us. So it's giving us vertical velocities. All right, and it's very similar to an altimeter in its internal look. The biggest difference between with these is that you have a leak. There's a leak in the case. There's a leak that allows the pressure to escape. So as the static pressure builds up inside, actually in this case the static pressure is going into this little wafer right here, this diaphragm right here. And then the outside, or the case itself, has a leak, so that as things expand or contract, it begins to leak. Okay. So what will happen is, as that needle says, "Oh, we're climbing," and then it starts leaking out, and the rate of leak stabilizes the needle into a rate of climb or descent. So the speed at which, if we're climbing at a constant rate or descending at a constant rate, which doesn't happen immediately when you start a climb or descent, the rate has not stabilized. The forces have not stabilized. Lift and weight aren't equal. All the up forces and all the down forces are not equalized, and you have an imbalance. And that's when that needle goes bing, bing, and it gives you an initial indication of climb or an initial indication of descent, but it takes a few seconds for it to stabilize into a rate. Once it has stabilized, your forces are back in equilibrium. You're in a constant speed condition. You're back in equilibrium. So you can be in unaccelerated steady state flight. In other words, lift equals weight, thrust equals drag. Once this thing stabilizes and your airspeed has stabilized, and these aren't bouncing, your forces are back in equilibrium. Okay. All right, that is, let's see what I have here. Oh, okay, yeah. So trend and rate. So it gives you two things. It gives you trend and rate. So if you initially pull back on the stick, you'll see the vertical speed indicator go ding. We're climbing, but you're not climbing at 2,000 feet per minute, right? It's just bing, we're climbing. And then it'll stabilize into what the actual rate is, as long as you're not doing this. If you're doing this, it's just doing this. But if you pitch and hold, it'll bing, and then it'll stabilize.
And that's the trend?
That's the trend. Well, that's the rate. The trend is, as soon as you make a pitch change, bing, it'll say you're going up, you're going down, and then it stabilizes into a rate. Yeah. Yep. Okay. All right, the airspeed indicator operation. We'll get through this here in the next 5 minutes, and we'll take a break. The airspeed indicator is it's a differential pressure gauge, so it's measuring the difference really between the ram air pressure and the static pressure, and it's reading out as dynamic pressure is what you're getting. So think about, I want you to think about, whenever you think about an airspeed indicator, really, it helps me anyway. Maybe it'll help you, maybe it won't, but it helps me. I think about the airspeed indicator as a pressure meter. It is a dynamic pressure meter. And in order for a wing to stay airborne, in order for a wing to develop enough lift to keep the airplane flying, I have to have a certain amount of dynamic pressure on that wing. So you can think about the airspeed indicator as a dynamic pressure kind of a meter, all right? We're going to get into true airspeeds in a minute, and it's going to get confusing, but we got to go there. All right, let's just go there. Let's go there. All right, so we talked about all the different types of altitudes. There's a lot of different types of airspeeds as well, so we got to talk about all these airspeeds. And I think what I'm going to do, rather than getting to them now, is let's just take the break about 5 minutes early, and then we'll come fresh and get into airspeeds, because there's a lot here. All right, we're going to get started again. All right, so let's talk about airspeed. So just like altitude, just like, you know, you'd think, well, what's your altitude? And there's a number, and that's the number. Well, just like airspeed. What's your airspeed? You think, well, I look at the airspeed indicator, that's my airspeed. Well, that would be great if that were true. It's just not true. We have lots of airspeeds. We actually have 5 airspeeds. We're only going to deal with 4 of them because we're not flying aircraft that approach the speed of sound. When you get into aircraft that get close to Mach 1, as you get up into the Mach speeds or close to Mach, the air becomes compressible, and now you have to have a different airspeed that you deal with called equivalent airspeed. But we don't have to worry with that one. So you guys are going to be future airline pilots. You got to worry about that later, but we're not going to worry about it today. So we're going to worry about 4 airspeeds, okay? And the first one we're going to worry about is indicated airspeed. What do you think indicated airspeed means? It's what it reads. It's what it reads, okay? So indicated airspeed is, what do you think? Think about the pitot-static system. What did I tell you that altimeter, what did I tell you that airspeed indicator was? It's a pressure meter, differential pressure meter. It's reading dynamic pressure. Okay, so indicated airspeed is basically the dynamic pressure. It's the dynamic pressure. It's what it is. Now, unlike an altimeter where you can adjust it so that what is indicated could mean different things, with the airspeed indicator, you can't adjust it. Okay? It is what's indicated, and what's indicated is the dynamic pressure. What's indicated is these 2 components of the lift formula right there. The pressure, the pressure, we'll just call it pressure and velocity. The pressure times the velocity. Okay? All right, that's indicated airspeed. The next airspeed is calibrated airspeed. So we have IAS, indicated airspeed. We have CAS, calibrated airspeed. Calibrated airspeed is indicated airspeed that has a correction factor applied to it or has been corrected. And it needs to be corrected for 2 things: instrument error and position error. Okay, so let's talk about what that means. If I take a pitot-static system, pitot tube and a static port, and I have, the static pressure and the ram air pressure, and it reads into an airspeed indicator, all right? If I take this in a laboratory setting and I have everything perfect, maybe I could get it to where I have very close to 0 instrument error in the system, if you could imagine that, right? And you're in a controlled environment, maybe you could get virtually no error out of the plumbing or out of the system in general. But now I take this and I put it in an airplane. I'm going to introduce some instrument error into the system. There's just going to be some amount of error in the system, okay? Probably not a really big error, but there's going to be some error in it, all right? That's instrument error. The other type of error is position error. And when we say position error, really what I want you to think about is, I want you to think about the pitot tube. Think about the pitot tube sticking out of the front of that wing, or wherever it is. Think about the airflow coming into this pitot tube. I want you to picture, visualize the molecules of air going into that pitot tube. You picturing it? Now picture it. Picture the molecules of air going into that pitot tube. Can you visualize a difference in the way the air, okay, this would be much closer to getting rid of any error, and this might increase some potential for error? Okay. So when we say calibrated airspeed, what we're doing is we have to correct a perfect system for instrument error and position error. Okay. You can't do that without going to the manufacturer's handbook, the pilot operating handbook, and looking up the airspeed calibration chart. The manufacturer has to have gone out and flight tested this thing and figured out what these errors are. So now you take this chart, this calibration chart, and this is a Cessna, okay, and they could be laid out a little bit differently, but they essentially follow the same format. In this case, it's saying, okay, if you're flying with flaps up, or if you're flying with flaps at 10 degrees, or if you're flying with flaps at 40 degrees. Let's just use flaps up for a second. What this is saying is, hey, if you're flying with the flaps up, and you're indicating your knots indicated airspeed versus knots calibrated airspeed. If you're indicating 140, and by the way, when do we fly fastest? Like this or like this? Like that. So when we're flying fastest, where's our pitot tube? Look at the difference. But when we're flying really slow, as we get slower, look how the difference, what happens? It increases. Can everyone visualize that? All right. So here's what I want you to take away from this. There's the practical takeaway from this. When you're flying in a cruise condition, in a small general aviation airplane that doesn't get anywhere close to compressibility, okay? If you're flying like this, your indicated airspeed is your calibrated airspeed. It's close enough. It's close enough, okay? That's what I want you to take away from this. But you need to understand what calibrated airspeed is. You need to understand that there is a difference, okay? And you need to understand and be able to defend why I'm telling you that indicated airspeed and calibrated airspeed are close enough that you can ignore calibrated when you're in cruise or close to cruise flight. Make sense? Okay, that's calibrated airspeed. So calibrated airspeed is indicated airspeed corrected. Oops, I went the wrong way. There we go. Calibrated airspeed is indicated airspeed corrected for position error and instrument error. All right, the next airspeed is true airspeed. Here's the one that blows everybody's mind. Yeah.
Did it actually increase when you're making the turn?
No. Airspeed? Airspeed will actually decrease in a level turn because you have to increase the angle of attack a little bit to maintain altitude, so you slow down when you're turning. Yeah. Yeah. Oh, you're saying the calibration error. The error. No, because when you're in the turn, there may be some slight difference, but it's not. No. Yeah, don't worry about it in a turn. Yeah. Okay, true airspeed. True airspeed now is calibrated airspeed. So as we're going through this airspeed, you're going to notice that you have to start with indicated, then you do something to get to calibrated, then you take calibrated and you do something to get to true. So you got to start here and then work your way through these airspeeds. True airspeed is calibrated airspeed corrected for temperature and pressure, non-standard temperature and pressure. All right. This one is the one that's hard. Sometimes it takes a little bit for people to perhaps understand. So let me do this because I really want you to get this. I see a lot of people not connecting the dots when we get into the stage checks, especially when we get into stage 2 and you start doing cross-country stuff. And I recognize pretty quickly when you're doing your cross-country navigation logs that you don't really understand true airspeed. This is where I really catch it, okay? So let's talk about this real quick. I'm gonna draw this formula. I'm gonna put this formula up here again. Okay, and we said that this is dynamic pressure. So this is what? Pressure. This equals true airspeed. Or excuse me, this equals, I'm sorry, this equals indicated airspeed, not true airspeed. Indicated airspeed. Okay, that's your indicated airspeed right there. Okay. So if I'm down here at sea level, and I hope if I start losing you, you got to stop me, okay? You got to be honest with me, because some of you are going to get lost here, and you got to stop me. All right. So if I'm down here at sea level, I'm flying along at 100 feet or so along the beach. Okay. Let me close this so you can see. I'm flying along here at 100 feet. You can see. And my indicated airspeed equals 100. So my pressure, my dynamic pressure meter is reading 100 units of speed, okay? Or 100 units of pressure, however you want to think about it, okay? My true airspeed, remember we're saying that indicated airspeed and calibrated airspeed are the same because we're flying in cruise. So we start with indicated airspeed, we get to calibrated, then we correct and then we go to true. But we're saying these two are the same because of the reason that I told you a while ago. Those are the same. I'm at sea level. It's a standard day. So what's the density down here? So 29.92, that's 29.92, or half 29.92, okay? We're at 29.92. And the temperature is 15 degrees Celsius, which keeps the pressure there. My true airspeed then would be 100. There would be no correction factor. So true airspeed is calibrated, which is true, corrected for non-standard pressure. So it should be 29.92, but it's not, so I got to correct for that. And non-standard temperature, so it should be 15, but it's not, so I got to correct for that. But in this case, they're the same. There is no difference. Therefore, my indicated and my true airspeed are the same. There's no correction factor.
Because it is standard.
It's because it's standard. There's nothing to change. All right. Now let's just arbitrarily jump up here to 10,000 feet. Okay. Now so this is sea level. This is 10,000 feet. Okay. We can Scotty beam me up to 10,000 feet, and boom, we just go to 10,000 feet. Our indicated airspeed isn't going to change. It's still going to be 100. But our true airspeed, even if it's a standard lapse rate, so what should the pressure be up here on a standard day? We talked about it a second ago. 19.92. Temperature up here should be -5. Okay. All right, so that would be the standard lapse. In that case, is the air thinner up here?
Yes.
Yes. So did this go up or down? It went down, therefore that's got to go up. True airspeed is 116. True airspeed went up simply because these have to be in balance. If this goes down, that goes up. If that goes up, that goes down. They have to offset each other. They got to offset each other. Okay? So on a standard day at 10,000 feet, if I'm indicating 100, my true airspeed would be 116, and mathematically that's just what it would be. I'm not I don't need to show you why that is, but that's what that would be. Does that make sense? Okay. So as the air gets thinner, as the density of the air thins out, as the molecules spread apart, the airplane moves faster. Its true airspeed, not its indicator. You're still going to indicate 100 in this example. But you will truly be moving faster through the air. That's the concept of true airspeed. So the thinner the air, the faster we're going to move through it. Our true airspeed will increase. Okay? If we could jump up to 40,000 feet, which this airplane would never get there, our true airspeed would be 200. We'd still be indicating 100. We look at our airspeed indicator, it would say 100, but our true airspeed would be 200. We'd be moving 200 across, well, I won't say across the ground. I'll say true airspeed. We'd be moving 200 units of speed.
So it's one of those, you have to watch your indicator also? make sure that you're not flying in the red?
Well, so that's the beautiful thing about an airspeed indicator. It's a pressure meter. So the dynamic pressure on the wing, what's going to rip the wings off? Dynamic pressure. Your dynamic pressure is still 100. But you're moving faster through the air, but the air is thinner, so you can actually go faster through it before it builds up that pressure that would cause damage. Okay? All right, so let's be more realistic. 10,000 feet. 116. Okay? Does that concept kind of stick? Is that sticky at all? The thinner the air, the faster we're going to move through it. Thinner the air, the faster you're going to move through it with the same amount of thrust force that you're putting into this thing, if you will. It's kind of like how many of you are swimmers? You swim in a pool, you swim in fresh water, it's kind of thin. If you're ever to go out to salt lakes, and you know, I mean, you float in that and you try swimming in that, you're not going to, you can put forth the same effort, but you're not going to move through it as fast as you move through thin water, right? So the thinner the air, the faster we're going to move through it with the same amount of input that we're putting into, is less resistance. We're going to move through it. Okay. Nobody said stop, so everybody got it, right? All right, I'm going to take it. So I'm trying to remember when I have you on a stage 2 check, I'm trying to remember everybody that didn't ask. Okay, the next one is ground speed. This is the last one, ground speed. This is where we ultimately want to get to. What's our ground speed? Ground speed is how fast are we moving over the ground. So to get the ground speed, we have to start with indicated airspeed. We have to correct for calibrated airspeed, which, remember, if we're in cruise, it's the same thing, so there's not really much of nothing we're really going to do there. Okay. Then we got to calculate true airspeed. Now we can calculate ground speed. So ground speed is true airspeed corrected for wind. Corrected for the wind. So let's go back to this example I have right here. Ground speed, ground speed. In these cases, down here, if there's no wind, there is zero wind on my nose or on my tail, what is my ground speed here? 100. What's my ground speed here? 116. 116. If I have wind in my face at 10, what's my ground speed here? What's my ground speed here? 106. If I have wind on my tail, what's my ground speed here?
How fast is it?
Huh?
How fast?
Oh, sorry, 10. Same, yeah, but on my tail. 110. 126. 126. So in order to calculate how fast we're moving over the ground, we got to get to true airspeed. You can't look at your airspeed indicator and say, well, I know I got a 30 knot tailwind and add 30 to what you see here. That doesn't work. It doesn't work. You got to adjust for temperature and pressure to figure out how thin is the air, how fast am I moving through this air. Now I adjust wind on my butt or on my nose. Okay? All right. No questions on that, huh? Okay. Yeah, go ahead.
Are you going to do the calculation?
I can't. We can do one if you guys want to do a calculation on that. You got your E6Bs?
Okay, that's what I was wondering. Are we going to need these?
Yeah, you need an E6B. So we do this when we do the E6B class and when we do navigation.
Okay.
So I'll show you how to calculate when we do those. Okay. All right. Let's look at the airspeed indicator and its markings. So aircraft weighing 12,500 pounds or less, and by the way, 12,500 pounds is what's classified as a light airplane. Any bigger than that, it's a heavy airplane. So if it's 12,500 pounds or less, and it was built after 1945, and FAA certified, are going to have these type of markings on it. Okay, and these markings will tell you, and let's pass an airspeed indicator around. Those markings will give you different ranges of operation. Okay, so we have white ranges, we have green ranges, we have yellow ranges, we have red lines. If we have a multi-engine airplane, we have blue lines. There's different color codings on airspeed indicators that mean different things, or that have meaning. Okay. The reason this is good is because you can get in any airplane. If you understand the color codings, then you can get in the airplane, look at the airspeed indicator, and have a lot of useful information right off the bat about what you can do and what kind of limitations there are on that particular airplane. All right, so we'll go through some of these speeds here. So the white range, when you see the white range, that's essentially where you can operate flaps. So as long as your indicated airspeed, as long as your dynamic pressure airspeed is in the white area someplace, then you can operate with the full deflection of flaps, all of the flaps. All right? Some airplanes will allow you to put some partial amount of flaps in, even when you're flying faster than the white arc or white range. But you have to get that information out of the operating handbook. Okay, so as an example, our GXs. GXs, you can operate with partial flaps at, I think, up to 115. But the G3, nope. You got to be at or below 80 before you put anything in. Okay, but both airspeed indicators, which is getting passed around now, show the white range starting at 80 on both the GX and the G3. What that means is that on any airplane is if you're not sure of that, then just don't put any flaps in until you're in the white range. Because once you're in the white range, you can put them all in. That's what that means. Okay. The green range or the green arc. So we're starting to call them ranges now. We used to always call them arcs because they were on an airspeed indicator and they were always arcs. But now on the flat screens are just lines, and we call them ranges. But the green range or green arc is the normal operating range. So that's where we're going to. That's as long as we stay within that range, we're not doing any real damage or have any issues with the airplane. The yellow range is the caution range. So here we can be flying in that range, but we have to be careful about structural things. If the air is extremely smooth, and I mean like there's not one little cottage cheese lump in it, it's more like yogurt. Okay, if there's any cottage cheese in there, you need to be in the green. If you're flying through a yogurt, you can be in the yellow. It's got to be perfectly smooth. Okay? And then the red range is don't go there. Don't go beyond this. You go here, now we have so much dynamic pressure built up on the aircraft that you can start bending and breaking things. There's so much pressure built up that you can start bending and breaking things. Especially if you get there and then you pull and you can break the wing. Okay? So you stay away from the red line. You only go in the yellow arc if it is really, really smooth. If it's not really, really smooth, you keep it in the green. Okay.
How would you know if it was really, really smooth? Just by feel?
You'll feel. Well, you're not going to have any. There's not going to be any
It's not
turbulence.
You're going to be able to read or anything?
No, you're going to feel it in the airplane if it's turbulent. If there's any turbulence, you hit any. Oh, let me get out of the yellow. There's nothing. It is perfectly smooth. You can stay. You can be in the yellow.
You hear the pilots on a commercial flight coming into turbulence. How do they know that? They're feeling it?
Oh no, they're knowing that because they're getting weather reports up ahead of them. They know it's coming. Yeah. Okay, and then at these ranges then we'll talk about the top and the bottom of ranges. So bottom, this would be the bottom of the white arc, the lowest speed of the white arc, or the top, the highest speed of the white arc, or the bottom of the green range, or the bottom of the green arc, or the top of the green arc. Okay, so we talk about tops and bottoms of ranges or arcs, and what we're talking about are specific V speeds. When you hear V speeds, and everybody here's heard V speeds, right? V speeds are velocities. So velocity, so VSO, VS1, VX, VY, VA, VNE, all these V speeds, okay? They represent specific speeds for specific airplanes, but they also correspond to specific places on an airspeed indicator. So when I look at the top of the white arc, that will always be VFE, velocity flaps extended. Okay? So I don't have to necessarily, I can be talking to somebody about that citation sitting out there. And if he said to me, VFE is 110 knots, I know exactly what he's talking about. That means that's the speed he's got to be at or below before he can put the flaps in, VFE, right? So we talk about these V speeds so that we can correlate them to limitations on the airplane. And then when we're flying whatever particular airplanes we're flying, we need to know what those numbers are. We need to get those numbers in our head that correspond to these V speeds, or we can simply look at the airspeed indicator and see some of those speeds by being represented by locations, color codings on the airspeed indicator. Okay? So that's how those work. So we'll go through the ones that are shown here. So the bottom of the white arc is always VSO. That's velocity stall in the landing configuration. So in other words, the flaps are out, full flaps, the gear is out, you're ready to land. That's the speed at which if we get below this dynamic pressure, the wing stops flying. We cease to produce enough of this. We cease to produce enough of that to overcome the weight vector. And we stall, essentially. You run out of dynamic pressure, you stall. That's what happens. Okay. That's the speed in a 1G condition, right? Remember we talked in the aerodynamics class, what speed does this airplane stall at? That's connected to this airspeed indicator. Any speed. It stalls when? Critical angle of attack. Don't be confused. Just because we list a stall speed, here's another stall speed I'll get to in a second. These two are stall speeds. Just because we list a stall speed, it only applies if you're pulling one force of gravity. Anytime you increase the force of gravity, what happens to the stall speed? Goes up. When you increase the wing loading, stall speed goes up. When you increase the force of gravity, you're increasing the wing loading. When that happens, stall speed goes up. So these only apply in a 1G condition. It's really important that you understand. All right, so VSO and VS1 are both stall speeds. You'll notice that VSO is the bottom of the white. VS1 is the bottom of the green. Okay, so this is the slowest speed you can go with the flaps in the landing configuration. Flaps are out, gears down, all that good stuff. This is the slowest speed you can go with the flaps up, gear up. So this is dirty from a drag standpoint. This is clean from a drag standpoint. The way to remember it is stuff out, stuff in. VSO, stuff out. VS1, stuff in. Okay. Sometimes you won't have VS1, sometimes it'll just be VS. The one just simply indicates some configuration. So VS is some clean configuration. So it could be, I'm just making this up, it could be VS1 is flaps out, VS2 is flaps and gear out or something like that. But when you have, VSO is always dirty, dirty, dirty. VS or VS1 is some clean form or another. Okay. So white arc, flap operating range, green arc, normal operating range. So the green arc, the bottom is VS1, that's stall clean. The top of the green arc is VNO. VNO, velocity, normal operating range. So it's the top of the normal operating range. So the bottom is VS1, the top is VNO. It's the normal operating range. The yellow arc does not have any V speeds associated other than you could say that the bottom is VNO and the top is VNE. So it's just called the caution range or the yellow range. You can be there, but what do the flight conditions have to be flying in there?
Yogurt.
Perfectly smooth. Yogurt, yeah, perfectly smooth. Perfectly smooth, okay. And then VNE, never exceed. Never exceed that speed. You exceed that speed and the pressure, the dynamic pressure that's being built up on the airframe increases to the point where you can do damage pretty quickly. Parts start falling off of the airplane if you get much faster than that. All right. Okay, let's see. Let's talk about blockage in the pitot-static system. What happens if the pitot-static system blocks? These are questions you could get on your written exam, okay? So you have to understand something about the pitot-static system that you have. First of all, you need to understand whether you have the biggest thing is a heated pitot tube. If you have a heated pitot tube, then that means that there's a little heating element in here such that if you're flying in, if your pitot tube ices up or something like that, you can turn on the heat to melt the ice so that your airspeed indicator continues to work. But in that case, you need a drain for the ice, the water to drain out of. You got to have a drain hole, okay? So if you have a heated pitot, that means there's a drain hole somewhere in that pitot tube. So now if your pitot tube gets blocked, what happens depends on where it's blocked. If it blocks up here and whatever pressures in the system is allowed to drain out that hole, you have one type of indication. If the blockage occurs up here and you keep the pressure in the altimeter, in the airspeed indicator, now you have a different type of indication that occurs. Okay? All right. So let's make some assumptions. You guys should be able to logic your way through this by now, by what we've talked about. You should all be able to just figure this out without me even going too deep into it. This is open. We're going to say that's not blocked. That's not blocked at all. But we have a pitot tube that does not have a drain hole. Our aircraft do not have drain holes. There's no drain holes in our pitot tube. So this is blocked. This is just one plumbing tube that goes right to the airspeed indicator. If we're flying along, let's say we're flying along, we're indicating 100. That shows 100 right there. We're at 4,000 feet and we're level. We're not climbing or descending. We're at 4,000 feet. We're at 100 indicated. We're flying along and a beetle hits that and blocks it. Okay, we're flying along and it just gets blocked. Okay, what's going to happen? Well, let's think about it. Are we getting any change in the pressure that we're flying at? Is there any change in static pressure? No, there's no change in static pressure. We have ram air pressure going in here and then we block it off. Are we changing the ram air pressure or did we just stop it up? We just stopped it up. It's like blowing up a balloon and stopping it up. We just stopped the amount of pressure that's in. Now if we take our thumb off, we let all the pressure out. But we blocked it and we're keeping the pressure in there. So what my altimeter is doing is reading, it's showing me the difference between the ram air pressure and the static air pressure. Well, I didn't change the ram air pressure, I just stopped it from changing. So what happens? Absolutely nothing. We just keep on flying and we have no idea that we have a blocked pitot tube. None whatsoever, okay? But now, think about what we have from a plumbing standpoint. What do we have? We have 3 instruments connected to what? That's it. They're all static port instruments now. If we climb, what does this do? If we climb, what does that do? If we climb, what will that do? It'll climb. It turns into a really shitty altimeter. That's what happens. It just goes up. What should happen to airspeed when you climb? It should go down. You pitch the nose up, the airspeed usually decreases in a climb, right? Well, in this case, it's going to start going up. And it'll just keep going up. It'll keep going up, right? What'll happen when you level off? Well, whatever airspeed it got up to when you level off, it'll stop right there. As you begin to descend, these will show properly because they're only connected to the static port, and this will show a decrease in airspeed as you're descending. And when you get back to 4,000 feet, it'll show 100. And as you descend below 4,000 feet, it'll show lower and lower and lower. It's an altimeter.
So is that a way of seeing if your airspeed indicator or if your pitot tube is blocked?
Well, if you have a pitot tube that doesn't have a drain hole, or if the blockage blocked back here, okay? If you're blocking the pressure in there, when you climb, your airspeed increases. When you descend, your airspeed decreases. Because now you're just connected to the static port. Increase, decrease, increase, pressure, up or down, increase, decrease. It's just a static instrument now. It's not reading ram air pressure. Does that make sense? Should make perfect sense. All it is now, it's just connected to the static port. So it's just acting like an altimeter, but it doesn't make any sense because it's not geared properly to read as an altimeter. It's just going up or down. It's just showing an indication of up or an indication of down. Okay. If you have a drain hole and your blockage occurs back here, Now it's like blowing up a balloon with a little hole in it. All that pressure just drains out. Now my altimeter is going to just peter out to zero, or it'll show something, but it won't show anything that resembles anything that has any logic to it. It's going to decrease to visibly show you I definitely have a problem with my airspeed indicator pretty quickly, because all that pressure that was in there now drains out. Does that make sense? Okay. All right. So that's okay. So that's what we were just talking about with the pitot tube. All right. Now let's look at a blocked system with clear static system. Okay, this is what we were talking about. I think I got it all, don't I? Yeah, this is basically showing you everything we just talked about. Okay. All right. Let's move over here real quick now, and let's go back and I want to just reintroduce you to these real quick. So airspeed indicator, right? Attitude indicator, altimeter, vertical speed indicator. All right. Now we're going to move into the gyroscopic instruments, but with a flat screen type setup, electronic display like this, these have what are called an air data computer. There's a little computer box back there. And the pitot tubes, or the pitot and static ports, the plumbing, rather than going to the individual instruments, are going into the back of this air data computer. And then all of this information, pressure information, ram air pressure and static pressure, is getting the computer's working with it and sending that out as the indications that we see. It's happening in the air data computer. Okay. All right. Let's talk about the gyroscopic instruments. What is a gyro? This is a gyro. Any spinning disc is a gyro. And the concept of a gyro is it wants to, as this gyro is spinning, it wants to stay in that plane. If I move it, see how it turns, see how it doesn't want to, I can move it, I can overcome it, but when I do, it processes, it moves. So it would want to stay right there. If I put it on a gimbal, if I put this on a gimbal and I had something else attached to it, I could move this thing around it without this moving. This wants to stay rigid in that plane in space. So the concept of a gyro is rigidity in space. So as the gyro spins, if I start it spinning in that plane, it wants to stay. I don't have the bearings set up real well there. It wants to stay in that plane. If I have it spinning in this plane, it wants to stay in that plane. Whatever plane it's in, it wants to stay spinning in that plane because of the gyroscopic forces that are occurring there. Okay? That's a gyro. So when we talk about gyroscopic instruments, they all have gyros in them. They all have these little spinning discs inside their spinning, all right? So I'll pass around. I don't have an attitude indicator, but I do have a heading indicator here with the case taken off of it. So you can see the heading indicator, and you can see the gyro. Right there is the gyro. All right, the vanes inside the gyro are actually would spin inside of here. Okay, I'll pass this around, but that's the gyro for a heading indicator right there. All right, so to get the gyro spinning, we got to have that. We got to get that thing spinning. So there's two ways to get that thing spinning. One is air pressure, vacuum pressure, and typically with your what I call the round gauge instruments, the steam gauges. Typically with a steam gauge type setup, we use what's called a vacuum pump to spin those gyros. So that's what I'm going to talk about here. So here we have the layout for the vacuum system, and we have the attitude indicator and we have the heading indicator attached to a vacuum pump. All right. What's missing from this is this guy. This is the other gyroscopic instrument. That's not on there, and I'll explain why in a minute. This is not typically part of the vacuum system. This one is typically electrically driven. So there's a gyro in here, but it's spinning electrically, not with air flow. And it's for redundancy, or it's for a backup, basically. If the vacuum system fails, you still have something there with which to give you some information. All right, so what happens when you have a vacuum system, when you have your gyroscopic instruments run by a vacuum system, you'll have these two typically plumbed to the vacuum system, and you'll have somewhere in there on the panel, you'll have a suction gauge. So you can measure, one of the checklist items will be check the suction gauge to make sure you're developing enough pressure, suction pressure, that you know that the air is flowing across those veins and the gyros are spinning fast enough to maintain rigidity in space. If they're spinning too slow, they'll tumble. If they're spinning fast, they'll stay in that plane that they're in. Okay? All right. So here's the concept of the rigidity in space. And what happens every time, and we talked about this with gyroscopic precession on the left turning tendencies. Remember, that's one of the tendencies we have as that propeller's turning. As you apply a force, the force is felt as though it's 90 degrees in the same plane of rotation. Same thing happens with gyroscopic instruments. They can precess. Typically, you find the problem here in your heading indicator, the one that I'm passing around there. Those will precess, and I'll tell you what you have to do with that here in just a minute. And then the third gyroscopic instrument is this guy. This is the turn indicator and the inclinometer. Turn indicator and inclinometer on this guy. This one is electrically driven, and the reason it's electrically driven is that in the event that you had a vacuum pump failure, your gyro, your attitude indicator, there's a seat back over here, William. Your gyro is going to tumble. Your gyro is going to just go, it's going to just fall off, right? Your heading indicator is just going to be doing whatever. It's going to be showing whatever it shows, which won't represent anything close to accurate. Can you fit in there all right? Yeah. Okay. So this becomes a backup, and at the very least, it gives you banking information. It doesn't give you bank angle. It gives you the direction that you're banking. It tells you at least I'm banking left or I'm banking right. It doesn't tell me that I'm banking at 5, 10, 20, 30 degrees, but it tells me I'm banking in this direction or I'm banking in that direction, okay? So it gives me turn direction, and it gives me rate of turn if I put the little wing on these little marks here. If I put the wing on those little marks, then I know that I'm turning at 3 degrees per second. Oop, forgot to turn that off. Sorry, guys. I'm turning at 3 degrees per second. So what that means is, regardless of my speed, my rate at 3 degrees per second would be that if I'm facing this way and I turn and I put the little wing on the thing, I'm going to turn like this, and in 2 minutes, I'm going to be back facing the same direction. So that is called a 2-minute turn, or a standard rate turn. So if you hear the term, give me a 2-minute turn, what they mean is give me a standard rate turn. So turn at 3 degrees per second. You do that by going to your turn coordinator and putting that little guy, that little wing right on that thing or on this thing, and you'll be at 3 degrees per second. Or sometimes you'll hear a half standard rate, which will be put it right in the middle, around 1.5 degrees per second. So standard rate or half standard rate, or wings level. If your wings level, you're not turning. But if you have even a 1 degree, you're going to turn. It'll be slower, but you'll be turning. All right, so the turn coordinator gives you two things. It gives you direction and rate, and the inclinometer gives you quality. This gives you the quality of the turn. This tells us whether we're slipping or skidding through the turn, through that ball right there. How many of you that are training right now look at that ball pretty frequently when you're in a turn or initiating a turn? Okay, I'm going to tell you to stop doing that. I'm going to tell you to stop doing that. You don't need to do that. I'm going to tell you how to do it here. So first of all, let's talk about a slip and a skid and what it is. If we're in a coordinated turn, whether we're left or right, that ball is going to be in the middle. This is a skidding turn, the ball's to the outside. This is a slipping turn, the ball's to the inside. So you can visualize it here. If we're turning here, if I'm going through this turn, look at the tail. Look at the line. Visualize the line that the nose is flying through, and visualize the line that the tail is flying through, and they're flying through the same line. In this case, the ball would be right in the middle. Okay? If I was skidding, or if I was slipping through that turn, it would look like this. The tail is falling out of the turn.
You actually be increasing your height at that point?
Nope, nope. You're staying level, but the line that the nose is going through, or you could be climbing or descending, but the point is the turn. The line that the nose is going through and the line that the tail is going through are two different turns, and that would be a slipping turn like, well, let me do it this way. That'd be a slipping turn like that. You turn it in the way that's going, okay? If I were skidding through the turn, this would be happening. And this is very dangerous. You don't want to skid through a turn, okay? All right, so what that ball is doing is it's showing you, it's essentially lining up the centrifugal force that happens in the turn. So if the centrifugal force is pointed directly in the, 90 degrees, if you will, out of that turn, I guess, maybe that's not the right way to say it, but the ball will be right in the middle. If you're kind of skidding through the turn, that ball kind of falls to the inside of the turn. If you're skidding through the turn, the ball gets slung to the outside of the turn. All right, here's the way I want you to do it from now on. Try and do this. First thing you have to do is get comfortable in the airplane. You got to get comfortable in the airplane. If you're nervous, if your knuckles get white holding the stick, this won't work for you. It won't work. You got to be comfortable. You got to be loose in the airplane. Get loose in your torso. Get loose in your torso. When you're sitting in the seat, and you're flying, your torso should be straight up and down the seat. When you turn, if you're coordinated, your torso will be straight up and down the seat. If you're slipping, if we're turning this way and I'm slipping, my torso will be falling to the inside of the turn, just like the ball will. If I'm skidding, my torso will be thrown to the outside of the turn, just like the ball will. So feel it in your torso. Don't look at the ball, just feel your torso. Am I falling in or am I skidding out of the turn? It's really that simple. Just feel it in your torso. But you got to be loose. You have to keep your torso loose, then you'll feel it. You never have to look at the ball. You'll never have to look at the ball again. You just don't. You don't need it. Feel it right here. And what does your instructor tell you to do with the ball? What if you see this? What are you going to do with that ball? You're going to step on it. What do you do with that ball? Okay, now take that to your torso. If I'm falling this way, am I going to use that leg? I'm going to use this leg. If I'm falling this way, I'm going to use this leg. Step on your torso. Just step on whichever way you're going. And it's not step on, it's apply a little bit of pressure. Just a little bit of pressure. Okay, so that's how you don't look at the ball.
Why is one more critical than the other?
Okay, so the reason it's more critical, a slip is a non-dangerous kind of event. You can turn with a slip. You can slip an airplane right down to the runway as long as you maintain dynamic pressure over the wings. It's all about, everything is about dynamic pressure, guys. Everything is about dynamic. As soon as you lose dynamic pressure, what happens? You stop flying. And how do we read dynamic pressure? What is our dynamic pressure meter, which is our airspeed indicator. That works as long as we're in 1G, right? So you be careful. If you're pulling Gs, if you're maneuvering and you have excess wing loading, you have increased wing loading, you have to understand that your dynamic pressure meter is going to stall at a faster airspeed. You have to understand that. Your speed's going to go up when you stall. But you still have that dynamic pressure meter there to work with. So here's the thing. It's all about, you could skid through a turn as long as you keep the pressure, right? But it's a dangerous place to be. If I'm turning low to the ground like this, let's say that I'm slipping through this turn. I'm slipping through this turn, okay? Which wing, you have air, if you will, kind of increasing flow over this one and decreasing flow over this one. Which wing of the two wings would stall first? This one here? Yeah, this one stall first, or this one would fly and you'd stall up in this direction, okay? If I'm skidding through the turn, which wing is going to stall first? This one? And you just roll over into the ground. So a skidding turn, you just roll right over into the ground. A slipping turn, you stall up and over and you have more time to recover. You can do something with it. But both of them are a situation where you got to keep your dynamic pressure going over both wings. Okay?
So those accidents that happen, like from base to final, are usually because of
Skidding turns. So the number one stall spin accident that kills more pilots than anything else is skidding stall spin accidents turning from base to final. So you're 200 feet off the ground, the stall occurs, you just roll right over and you just, that's it right there. It's all over, right there. Skidding turns. Do not skid. Don't skid the airplane. Just don't skid. Slips are okay. Slips are something that you're going to use. That's a trick that should be in your trick bag, and everybody in here needs to know how to slip and when to slip and be comfortable slipping. Skidding, unless you're going to be an aerobatic pilot, and then you're going to be skidding all the time, doing all kinds of stuff. Unless you're flying aerobatics, you should never be skidding through a turn. There's no reason to skid through a turn. Don't do it. All right, that's your turn coordinator, and it operates also with a gyro, but it's electrically driven as opposed to vacuum driven. All right, let's look at the attitude indicator and the gyro and the attitude indicator. So the gyro and the attitude indicator is spinning in this direction, but it has a couple of gimbals around it, so it's spinning like this, okay, in the instrument. And what happens because of the gimbals is that this stays stationary. So when you pitch the nose up, the airplane is moving around the gimbal. The gimbal stays, the gyro. The gyro stays right there. The airplane pitches up and the gyro inside it stays right there. Airplane pitches down, the gyro stays right there. The airplane rolls, the gyro stays right there. So the gyro, this horizontal gyro, becomes the horizon. So this is the horizon that gyro spinning, and the airplane pitches and rolls around it, and that's how we get an indication of where's the horizon at. Because we have that gyro spinning parallel to the horizon, and all our pitch, roll, and yaw is around that spinning gyro. Okay? And we have a system of gimbals that allows us to do pitch and roll around this horizontally spinning disc inside the instrument. And the airplane's moving around that gyro in space.
When would the attitude indicator fail?
Well, it could fail if you have a vacuum pump failure. And now we don't have enough air spinning that gyro. There's not enough airflow spinning that gyro. Once the gyro stops spinning, well, now it's just going to tumble. And you're not getting.
How do you fix that in midair?
You don't. If you're flying VFR, you don't need this. You look outside because you got a horizon. If you're flying IFR, who's got the turn coordinator? If you're flying IFR, you transition to this guy to get your bank information, and you transfer to your airspeed indicator to get your pitch information. As long as you don't have a blocked pitot tube. If you got a blocked pitot tube and this fails, you're screwed. Okay. Some indications of your attitude indicator, and again, we have the same thing this is the one instrument that lines up pretty much the same, whether you're looking at a round gauge or you're looking at a flat screen. They pretty much laid out the same way. So you have pitch and bank information. It is when you're flying on instruments or you're flying in inclement weather, you can't see outside. That becomes really the center of your scan because it's giving you the most information at one time. You get pitch and bank information. All right. Just be careful because you need more than just this instrument to tell stuff. So for instance here, this says climbing right bank. Well, that's not necessarily the case. This is a nose up pitch with a right bank. You could be descending here, or you could be level there. So just because your nose is above the horizon does not mean you're climbing, right? Because you could be flying like this right here. Straight climb. Well, I could be flying level like that. I'm not climbing, but my nose is up. So whether I'm climbing or not, I have to reference other instruments. I can't just look at this and get the whole picture. I have to look at other things to get the whole picture. So this does not tell you whether you're climbing necessarily. Okay, it tells you what the pitch is. It tells you whether you're banking left or right. So if you're banking, you know you're turning. But it doesn't really tell you, I don't like this, it doesn't tell you you're climbing, it just tells you your nose is up and you're banked. You have to look at other instruments to tell whether you're climbing. Okay, heading indicator, the heading indicator, same thing, you have a gyro in there, but it's spinning vertically. It's spinning vertically. And so since it's spinning like this, as we turn the airplane, it stays there, and the way the linkages in the gears cause a compass rose to turn around it to give us indication of heading. All right. This one is really susceptible to precession. So if you're flying an airplane with steam gauges that has one of, let me see the one with the, yeah, that one right there. If you're flying an airplane that has this instrument, okay, this one's broken, but there's a knob there where you could turn it, you could adjust the heading on it. If you're flying one of these, what you do is when you start the engine up, as soon as you start the engine, the vacuum pump starts going and it starts spinning the gyro, and you'll hear zzz, you'll hear the gyro spinning up. But until you have adequate vacuum pressure, you can't really do much with this. Once you have adequate vacuum pressure, what you'll do while the airplane is stopped is you look up at your magnetic compass and you see what that reads, and then you set this to equal that. So they read the same thing. Then you go fly. Every time you, while you're flying, when you're making turns, you're introducing forces to that gyro and causing it to precess, causing it to precess, causing it to precess. So a good rule of thumb is every 15, 20 minutes while you're flying, you reset your heading. You look at the compass and you adjust this to get it back in matching your magnetic compass. And the more maneuvering you're doing, the more you're causing precession, the more frequently you go wings level, wait for your wet compass to stabilize, and then reset your gyroscopic compass.
Why would they change that?
Why would what change? Due to precession. So precession, so I'll let you do this. So hold it like this, okay? Spin it, all right, and then just move it. You feel the force. That's precession. So as it's processing, it's causing the heading indicator to read the wrong thing. It's just the gyro is processing every time. Because I'm just flying straight and level, I'm not really doing much with it. It kind of stays right there. But as soon as I turn, boom, I get a little precession. Turn again, get a little precession. Turn, get a little precession. It's changing the heading indicator a little bit. So every 15, 20 minutes, just get in level flight, let your compass kind of stay, your wet compass stabilize, and then reset your heading indicator.
So with the electronic panel, is there multiple gyros in the?
The electronic panel, you don't have to do any of that precession resetting. Yeah, yeah. Because there's not an actual gyro spinning in there. It uses what's called a magnetometer. It's a different. So the air data computer from a pedostatic system, the air data computer, you actually plumb it into the computer. But the gyroscopic stuff is done without physical gyros.
Same with the attitude.
Yep, there's no physical gyros in there. Okay, all right, now let's talk about the magnetic compass. This is not part of the six-pack, but it is in every airplane. You're going to have a magnetic compass in every airplane. In fact, when you look at the document, when you look at equipment that's required in the airplane, a magnetic compass is part of the A tomato flames. The M is the magnetic compass. So you got to have a magnetic compass. Oldest and simplest instrument, indicates direction, magnetic direction, but it has a lot of errors associated with it. So let's talk about all of these errors associated with the magnetic compass. So we have induced errors. So we have variation. Variation is one error that we have to deal with, and that's the difference between magnetic north and true north. So when we get to the navigation class, we'll look at this more deeply, but it is essentially when we want to go north, if I said let's drive, walk, fly, sail, whatever, north, then what we all think about is I want to go to the North Pole, right? I want to go right there. That's what we all think, right? When we say north. The problem is if I'm here on the globe, the way I would get north is I would use a magnetic compass. And I would keep that thing pointed to N, and that should take me directly to the North Pole. The problem is the magnetic forces come from over here somewhere, and the compass will take me here to magnetic north, not true north. So this difference, this angular difference right here is the variation. So the difference, whatever the angular difference is between where the magnetic poles emanate, magnetic forces emanate, the magnetic pole, North Pole, versus the geographic true North Pole, right? That angular difference is variation. And that angular difference depends on where on the globe you are. So you have to reference other sources, charts, basically, navigation charts to get that information. It's easy to get, but that's just one error that you have to be familiar with magnetic compasses. This is an old drawing. I don't know, this is probably quite old, but anyway, whenever this was done, I don't think it's on here, but this line right here, this 0 line, is what's called the agonic line. And so if you're on that line, then magnetic north and true north actually line up. But anywhere off of that line, you have differences. So you have east and west variation differences that you have to apply to navigation stuff to get where you want to go. I'm running long, so I'm going to just jump to this real quick. This is a sectional chart, and you can see on the sectional chart there are these lines, magenta dashed lines. Those are your lines of variation right there, and they're right on the chart. So here you have 3 degrees east, 3 minutes 30 seconds east, so 3.5 degrees east. 4 degrees east. Over here you'd have 4.5 degrees east, so forth. Yeah, so forth and so on. And then you just take that, depending on where you're flying, you take that number and you apply it for variation to your calculations. We'll do this when we get to navigation, but I just want to show you that that's a compass error. Then we have deviation. Deviation is, so we have variation, which is this, the variance between true north and magnetic north, and we have deviation, and deviation is how much the compass will deviate from north based on the stuff that's around it. So if I take this compass, and let's say out here in the middle of nowhere, it points to north. Let me get north here. And you'll notice these just bounce around too. The other thing with these is they just bounce around, so they're hard to read. But if you have it pointed north, let's say, I'm not going to wait for it. Let's say that's generally north right there. I have it pointed north. And then I take this compass and I go get into the airplane and I set it up on the instrument panel. It's going to go zip, or zip. It's going to do something. It's going to deviate some amount because I have metal stuff in that airplane. I turn the radios on, zip, it does something else, right? So I have some deviation that occurs to the compass because of where I mount it in the airplane. That's deviation. We have to account for deviation. The way we account for deviation in airplanes that don't have magnetometers is that you have what's called a compass deviation card somewhere near the compass. And the compass deviation card is divided up into 30-degree increments from 0 all the way back around to 0. All right? So 0, 30, 60, 91 to all the way 330 back to 360 or 0. All right? And all this is saying is once you've calculated, you've done your cross-country planning, and you've calculated your true course, or I want to go, let's say east. I want to go 090 is my direction that I'm trying to go. And I want to apply a deviation factor to it. Well, I'm going to go over here, find the 090. For this airplane, this compass, and where it's located in the airplane, I'm going to look at the compass card, I'm going to look down and say, okay, well, with the radios on, I need to add 5 degrees to that. So my compass heading is not going to be 090, it's going to be 095 because I'm accounting for the deviation, the junk in the airplane that's causing it to deviate or drift a little bit. So what you do is you find the heading within 30 degrees, the closest to 15 degrees of where you want to go, and you use that deviation factor. You apply that. We'll do this again in the cross-country flight planning as well.
In our planes, we don't have that, right?
We don't have it because we have a magnetometer. Yeah. All right, and then this is how these compass cards are developed. You may have seen, if you haven't, at some point you'll see, some airports will have these giant compass roses painted on the ramps. If you haven't seen them, at some point you're flying here, you'll see them. Some airports they have these big giant compass roses, and they're laid out to magnetic headings in 30-degree increments. And what a mechanic does, if they move the compass or they change instrumentation such that the deviation might change, they get a new compass card and they take the plane out there and they physically put the plane right there pointed north and they read the compass. And whatever it says, let's say it's this one, and the compass says 1 degree with the 2 degrees with the radio off. They put 2 degrees here, they turn the radio off, oh, 1 degree. Then they spin it 30 degrees. And they read the compass and they write it down and they spin it and spin it and spin it. So they just physically figure out what is the deviation based on a known true magnetic heading and what is my compass saying when I put the airplane here. That's all they do. That's how you come up, that's where you come up with these deviation cards. All right. Let's take, we're a little late on this break. Let's take a break here. Let's try and do it quick if you can, because I'm definitely, as usual, running out of time. Okay, let's finish up with errors, compass errors. We're just getting started with compass errors. So we have what are called dip errors with a compass. So let me diagram something here. Actually, I'll use this already, what I have here. Kind of like this. Let's say that here's the magnetic fields, okay? And let's say that we're flying down here around the equator, okay? So our plane is flying along the equator, flying north, okay? And inside the compass, inside the wet compass, we have a magnet bar, let's say, magnet bar. You guys have played with compasses, right, as kids. And you can magnetize a needle and put it on a piece of tissue paper and water, and it'll do its thing. Okay, so let's say this is the magnetized piece in the compass. It's in a wet compass. It's in a fluid, and one way to keep it from bouncing around too much is to have a weight on the end of that thing. So we take this guy and we put a weight down here. Let's say, we'll call that the weight. So that keeps it from bouncing too much. That weight tries to keep it stabilized, but it can still turn in that fluid. That make sense? Okay. So picture that inside the wet compass. All right, so here's my magnetized piece that's pointing at north. And here's my weight hanging off the bottom of it, keeping it stabilized. And I'm around the equator. But as I get closer to the North Pole, the magnetized end wants to point down towards the North Pole, and my weight gets shifted way back over here. Now every time I turn, that weight causes the compass to swing around in weird ways that would not happen when I'm at the equator and the weight's pointed straight down. So when I'm at the equator, I don't get any dip errors. But the closer I get to the North Pole, the more dip, the more the magnetized end dips down towards that magnetic north, the more the weight's way back here, and it'll cause the thing to shift around. Does that make sense? Okay, that's how you get dip errors, because you got this weight, and it's just causing havoc back there inside the compass. All right, so now let's talk about the dip errors and what they are. And we call them, and they're turning errors. Okay, turning errors and acceleration errors. Get this jacket off, it's getting warm in here. They're turning errors and acceleration errors. So the first one is turning errors, northerly turning errors is what we're talking about here. So there's a couple of acronyms that we can use to memorize these northerly turning errors. And the acronym is UNOS. You guys ever played that game Uno? Okay, UNOS. All right, and what you want to remember is undershoot, north, undershoot north, overshoot south. South. Okay, that'll give you your turning errors. Overshoot north, undershoot south. All right, so what you want to do is, as you're turning generally from an east or west heading to a north or a south heading, you want to undershoot or overshoot your turn. In other words, what the wet compass, and this is only to do with the wet compass. Okay, and as you understand these, you're going to understand why you love a gyroscopic heading indicator. Because as you're making turns, as you're flying, your gyroscopic heading indicator is not doing this, bouncing all over the place. It's nice and steady. Okay, but if you have to resort to this, if you lost your gyro, you're flying with this, you need to understand these. Okay. Okay, so undershoot north means that what you're reading on your compass, you're going to undershoot where you really want to go. So let's say you're going from a heading of east, due east, and you want to turn left and go to the north. Okay, so you're turning north. You want to undershoot your turn. Okay, so rather than turning until your compass reads north, if you turn until your compass reads north, then you've turned too far. And you'll have to turn back. So you want to stop your turn. You want to undershoot it by some degree, and then you're going north. If you're turning south and you want to turn right to the south, now you're going to overshoot. So if you turn and you stop turning when your compass reads south, you haven't turned far enough. You've got to go a little bit farther. That all has to do with that dip. It's all because that weight is back here instead of straight down. Instead of the CG being here, it's back here, and so it causes the compass to swing in weird ways. All right? So where's that going to be worse? Where does it exist at? Where does it not exist? Where do turning errors not exist? At the equator. So where are they going to be the maximum? At the poles. So the farther away you are from the equator, the more they're going to be. So there's got to be some kind of a thumbnail thing that we use to determine how much do we undershoot or overshoot, and that's real simple. It's right here. So how much does it lead or lag? What you want to know is what is the latitude that we're flying at. So what latitude are we at here? About 30 degrees? Somewhere around 30 degrees north latitude? So take the latitude, take half the latitude and add 15. So that's your lead or lag. Half the latitude plus 15. Is that what that says? Right here. It says it in here. So around here, flying around here, your lead and lag would be about 30 degrees. You're going to take half 30, 15 plus 15 is 30. So that would mean if I'm turning north, if I'm going from this easterly heading to a northerly head, so I'm at 90 and I want to go to 0, then I'm going to roll out when I get to 30. When my compass reads 30, I'm going to stop my turn. If I'm going the other way, if I'm going to south, I'm going to turn until I get to 200 degrees, 30 degrees beyond 180, or 210, 30 degrees beyond 180, and I should roll out somewhere close to 180. Okay? So that's your practical application with this. If you're having to fly, if you're making your turns based on the magnetic compass, it's going to lead or lag based, if you're on an easterly, westerly heading and you're turning north or south. If you're turning north, undershoot your turn. If you're turning south, overshoot your turn. Undershoot to the north, overshoot to the south.
Right here with 30 degrees, we're going like, north or south. If we're going like on a southeastern, northwestern direction, would we still aim for the 30 degree, or would it become actually like shorter?
Same thing.
Same thing.
Yeah, if you're heading in an easterly or westerly direction and you're turning northerly, southerly, then you have a lead lag issue going on.
Of that 30 degrees, if here.
If you're here.
Yes.
Half the latitude plus 15 is a thumbnail estimate. So if you're flying up at 60 degrees latitude, up or down at whatever, north or south, 60 degrees, you're going to take 45 degree lead or lag. So whatever your latitude that you're flying at, take half of that, add 15, that's the amount you lead or lag your turn. So you're going to undershoot a turn to the north, you're going to overshoot a turn to the south by an amount of approximately, it's not exact, but it's just pretty close, approximately 1/2 the latitude plus 15 degrees. And you'll roll out pretty close to where you want to be. It won't be perfect, but you'll be close. Okay. All right, and then southerly turning errors. I already talked about it, right? So you got northerly and southerly turning errors. Now we have another thing called acceleration error, and again, this has to do with the fact that the weight is back here or there or somewhere. It's not straight down. And so since it's not pointing straight down, when we accelerate, it can cause it to spin. It can cause it to do something. When we decelerate, it causes it to do something, okay? All right. So the acceleration acronym is ANDS. So that's accelerate north, decelerate south. Okay, so if you're on an easterly or westerly heading, and you accelerate, the compass is going to momentarily show a turn to the north. If you're on an easterly or westerly heading and you decelerate, it's going to show a turn to the south. Accelerate north, decelerate south. Okay. So some things in aviation, a lot of things in aviation, you want to get well past rote memorization and into understanding application and correlation. This is one where if at least you stay in the rote place, you're probably okay. At least if you stay in the rote place, at least you know what to do. It'd be great if you can get beyond it and understand, hey, that weight, that's what's causing this to happen. That'll help you understand it much better. But you at the very least need to understand that if you're flying with a magnetic compass, and you have an easterly or westerly, all of these have to do with easterly or westerly headings, okay? And you want to make a turn to the north, you need to undershoot that turn. You want to make a turn to the south, you got to overshoot that turn if you're using the magnetic compass. If you accelerate or decelerate, you're going to turn, the compass is going to show a momentary turn to the north, and then it'll come back. Decelerate, it's going to show a turn to the south, and it'll come back. Okay? And then the last error on the compass, there's a bunch of compass errors, is oscillation error. And that's just very simply this. I mean, that's just this. When you're trying to fly. And that thing's bouncing all over the place. It's just oscillating all over the place. That's oscillation error. And it's aggravating if you're trying to use that. Okay? So what I tell students to do is look at the compass. And if it's swinging between 180 and 210, 30-degree swing, then you're, in the middle. Just take your extremes and figure you're in the middle. Average, go to the middle. That's the best you can do when it's oscillating. Just get your extremes and figure, all right, I'm in the middle. That's where I'm at. Okay? All right. And then the last one we'll deal with here is a vertical card compass. So this is nice because this is actually a magnetic compass. It's a very expensive magnetic compass that acts just like a heading indicator. So it's not subject to all these turning errors, dip errors, and oscillation errors. But it's a really expensive compass, but well worth it. Okay. So it is a magnetic compass, but it turns nice. It just works just like a heading indicator. All right, the last instrument that I'm going to talk about, this isn't a flight instrument, so I have gotten into a couple, this is a little different than flight instrument, but this is outside air temperature gauge. So your airplane should have an outside air temperature gauge somewhere, and you should know where that is, okay? And a lot of planes, it's up, in Cessna's like it's up near the window on the top of the windscreen. And ours just reads on the screen. There's a temperature probe that sticks out the bottom of the fuselage. All right, so why do you think we need an outside air temperature gauge?
Calculate for speeds and altitude.
You need that to come up with true airspeed and density altitude. If you don't know what the temperature is, you can't calculate true airspeed or density altitude. So you got to have an outside air temperature gauge. So that's going to be there. All right. Any questions? Any questions on flight instruments? Turn vectors. Oh, thank you. See, look at that. I wrote it up there and I didn't do it. All right. So the turn vectors. Let me go back to this one, even though this isn't our layout. On our aircraft, so you have turn vectors. And on ours, trend vectors. Yeah, trend vectors. But it's on the turn.
Oh.
Yeah. The other trend vector is on vertical speed.
Oh.
So a trend vector on the vertical speed is you pitch it, you pull a stick back and you get a ping and you know you're moving in that direction, right? But on our plane, if you don't have the heading indicator, which would show up over here, you always have compass indication across the top. Have you guys ever noticed that? You get a compass indication across the top. You have a couple of brackets up there. I wish I should probably get a picture of the Dynon up there in my slide deck. But at the top, you have, let me draw this kind of large here. So we have our heading indicator over here. You have your attitude indicator there, airspeed, altitude with vertical speed. Here, you're either the little pink line's either going up or the pink line's going down. And where it stops at, it shows you the rate of climb or descent. Up at the top, we have heading. So these will be heading numbers, which would correspond to the heading, around the compass here. Okay. Just below the row of magnetic headings up here, you'll see a little bracket here and a little bracket here, and a line right in the middle. The line right in the middle is whatever heading you happen to be, whatever it shows right there. So if you're at 360 degrees, this right here shows 360 degrees. So you're heading north. All right. When you bank the airplane, as soon as you bank the airplane, you will see a little pink line, just like this, go in whichever direction you're turning. And the length of that line gives you, this fact that it's moving that way gives you trend. And where it stops at tells you where you're going to be in 6 seconds on our airplane. So if you turn to the right in this case, until this is under whatever that number is right there, that's where you're going to be in 6 seconds. That's where the turn will be. Okay. The trend is just where is it going? I'm going left or I'm right. I'm going up or I'm down. When it stabilizes and stops, now rate per minute, up or down, where am I going to be in 6 seconds? Okay. If you get this all the way out and stop it at the brackets, what do you think that is? That's a standard rate turn. It's 3 degrees per second. So if you turn this way and you stop it right there, 2 minutes later, you're going to be back at 360. So this becomes your turn coordinator, your rate of turn indicator. Okay? Thank you for asking that question. Okay. Let's go. All right, so we're going to move to documents. I got a half an hour, and I'm going to try and get through documents here real quick. I'm going to abbreviate it probably some. Not some, I'm definitely going to be abbreviate it. Flight manuals and other documents. Yeah, let me tell you what I'm going to do. What I'm going to do is I'm going to talk about, since I don't have time to do it all, let me talk about probably maybe one of the most important documents is the Airplane Flying Handbook, the AFM, or the POH, Pilot Operating Handbook, or the Approved Airplane Flying Handbook, POH, okay? Those are documents that are published by the manufacturer, okay? And it gives you the information you need about that airplane. It's going to give you the limitations, the operating limitations and speeds and all of the design stuff that you need to know from a piloting standpoint about that airplane. Performance information, all that kind of stuff. In aircraft that are normally certificated, okay, so this is going to be a little confusing. Let me try and break it down into 2 categories for you. You have normally certificated airplanes, okay? And then you have specially certificated airplanes. So special certifications could be things like experimental airplanes with an experimental certificate, special light sport airplanes like my airplanes. The new Mosaic stuff would all be special, could be, not are, could be special light sport airplanes. So the type of certification, whether it has normal certification or special certification, makes a difference in what documents have to be on board the airplane. All right? So everybody here that has started flight training, raise your hand if you've started flight training. All right. What's the acronym for the documents that have to be on board the airplane? Aero. And I'm going to do it with one R. Okay. Airworthiness certificate. Registration. Okay, here's where the confusion comes in. So we have operating limitations or POH or AFM, the approved AFM or POH, one of these two. Okay. The difference is whether or not this is a special light sport airplane, in which case this certificate up here is either going to be, this airworthiness certificate is either going to be on a pink piece of paper or a white piece of paper. If it's pink, you need operating limitations. If it's white, you need that. Okay? So if it's a standard certificate, let me finish what this is. W is weight and balance. Weight and balance information or document, okay? Next week we're doing weight and balance, so we're going to dig into this really deeply next week, okay? And you'll understand why this document has to be on, you're going to understand completely why this document must be on board the airplane for it to be legal. So from a documents standpoint, to have an airworthy airplane, we need these 4 documents. We need the airworthiness certificate, we need the registration, we need either an operating limitations if it's a specially certificated aircraft, if it's got a pink certificate, or we need the POH, the approved pilot operating handbook, airplane flying handbook, or airplane flight manual or pilot operating handbook. Okay, the approved one. What I mean by approved is that it is it has the information specific to that airplane. So I can go buy a manual, let's say for a Skyhawk, a 172. I could go online and buy a 1975 Skyhawk POH and have it delivered to my door. And that is a generic pilot operating handbook for any 1975 model Skyhawk. But it's not the approved manual that would necessarily need to be in, let's say there's a 1975 Skyhawk sitting out here on the ramp. Will the one that I bought, will the performance data and all that stuff apply to that airplane? Yep, sure will. But it's not approved. It cannot take the place of this. The one that has to be in that airplane is approved, and it has that airplane's serial number and registration number stamped in it, and it has specific information about that specific November 1234 Bravo airplane, serial number 522, sitting out there on the ramp, as opposed to some generic handbook. Does that make sense?
How do you get that one?
That has to come from the manufacturer when you bought the airplane.
What if you lose it?
You got to get it you could recreate it and get it. All right, so that's the difference between the POH and the operating limitations. Go ahead, were you going to say something?
POH for the Remos, I noticed the generic one doesn't have any of the weight and balance stuff in it.
No. Well, it does. It has weight and balance information, but it doesn't have specific to that airplane. So a generic POH for a Skyhawk will have weight and balance information, but not specific for that airplane. Okay. All right. So operating limitations on with an aircraft that has a special airworthiness certificate will be just that, the operating limitations. And it's usually 1, 2, or 3 page document, just typed up document on letters, paper, just, giving you the limitations for that airplane. All right. Then you have weight and balance data, which we'll go into heavily next week. All right. All right. Those are the documents that need to be on board the airplane. That's what we just talked about here. Developed by the aircraft manufacturer, approved by the FAA. Okay, that's what we talked about there. All right, the next thing that I want to talk about from the standpoint of legal documents, if you will, on the airplane, or legal things in the airplane, are placards. If you see a placard on an airplane, a sticker or a piece of metal with something inscribed on it, with a limitation on that, you got to follow it. It's not a, well, this might be a good thing to do. It's as if you pull this out and you put it in the approved airplane flying handbook, or you staple it to the operating limitations. It's part of the legal requirements for that airplane. So if you get an airplane like ours and it says no spins, it is illegal to go do spins in that airplane. Doesn't mean the airplane couldn't do spins, but it's illegal from a certification standpoint to do spins in that airplane. You can't fly into, if it says flight into known icing conditions prohibited, you can't fly it into known icing conditions. So anything, any placard in an airplane becomes a part of the certification, part of what is required, part of the things that you have to do for that airplane. Whatever it says, you got to, that is, it's as if it came right out of the POH or the operating limitations. Okay, so placards are, could be due to, yes, could be structural limitations, could be,
Who's enforcing it is my question.
I'm sorry?
Who's enforcing them?
Well, everything with flying is after the fact kind of stuff, really, with flying. It's when something bad happens that you get in trouble, because then they go back and say, well, you didn't conform to this, that, or the other. Typically that's what happens. All right.
These are the same placards as like if the location wasn't working, but like in operation.
Yeah, that's a placard. So we're placarding that. Now, when you placard something like that, you also have to do something in the log. I'm going to talk about that now in the log books. Okay. So let's talk about airworthiness now. Okay. We cannot fly an airplane. No person may operate a civil aircraft unless it is in an airworthy condition. The pilot in command of a civil aircraft is responsible for determining whether that aircraft is in condition for safe flight. The pilot in command shall discontinue the flight when unairworthy mechanical, electrical, or structural conditions occur. So 91.7, civil aircraft airworthiness. So let's talk about airworthiness real quick, okay? Specifically, I want to talk about continued airworthiness. So when an airplane rolls off the factory line and the FAA issues its airworthiness certificate, you can think about the airworthiness certificate, just everybody in this room has a birth certificate signifying that I was born on this day and I'm alive. An airworthiness certificate is just like that. This airplane was born on this day and it is alive. And it has a valid airworthiness certificate. Okay. Think about an airworthiness certificate like that. In order for the airplane to be legal to fly, it has to be maintained in a continued airworthiness condition. And there are things we have to do to make sure that we have continued airworthiness in this airplane. So a good example would be a Skyhawk rolls off the line, the FAA does their inspection, they issue the airworthiness certificate, they put it in the airplane, they roll it out on the ramp, and a fuel truck hits it, bends the wing. It has a valid airworthiness certificate in it. Is it airworthy? No, it just became unairworthy. It is no longer in a continued airworthiness condition. So just because you have this certificate doesn't mean it's airworthy. But in order for it to be airworthy, you have to have the certificate. Okay? So that's you need it, but it does, that in and of itself doesn't mean you're in an airworthy condition. So how do we maintain continued airworthiness? Well, one is we need to have some specific documents on board the airplane. And those are the documents I just wrote over there. The other R, which I don't use, is a radio certificate. That's if you're flying on international. If you're going to fly to Mexico or Canada or something, you got to have a radio station license in there. If you're staying in the United States, you don't need the second R. So airworthiness certificate, registration. The registration, by the way, that's like your license plate on your car. That's the N number on the side of the airplane. That's the registration. So you could buy an airplane that's registered 1234 Bravo, and you could put it from the FAA, say you want it to be 54321 Zulu, and you could change the registration. You can do that. It's like a license plate. Okay. But the registration certificate has to be in the airplane, just like if you get pulled over for speeding, they say license and registration. They want to see the registration for your car, the registration for the airplane. It has an expiration date of every 7 years. Every 7 years, you got to re-register. You got to have a new registration. You don't have to change the IN number, but you got to re-register. Unlike an airworthiness certificate, what's the expiration date on your birth certificate? There's not one on this either. But when you die, you know you're not walking around anymore, right? So it's not valid anymore. Okay. All right. But your registration you have to renew. The operator's manual or the operating limitations, if it's a special light sport or if it has a special certification. It's specific for that airplane, and any placards or deviation cards, external data plates, all of that are part of the operating manual. Or all of that's part of the operating manual or operating limitations on the airplane. That has to be on board the airplane. And then the weight and balance, current specific to your airplane, has to be on board the airplane. Again, we're going to spend 3 hours on that next week, so we'll talk about that in detail. So from a documents standpoint, that's what you need. ARROW. We use all these acronyms in aviation, right? A lot of acronyms. So one thing, I don't have it on here, but one thing I do for continued airworthiness, the main acronym I use is DIE, such that you might die if you fly an airplane that is not airworthy. So you have documents, and that is ARROW. Okay, that's ARROW. The next thing we have for airworthiness that we need to be concerned with are inspections. That's the I. Inspections. And under inspections, we have Aviate. That's the acronym we use for inspections. So there are certain inspections that must have been done at certain intervals on the airplane to maintain airworthiness condition. To maintain a continued airworthiness condition. And they will depend on the type of, and in some cases, they'll depend on where you tend to use the plane and what type of conditions you intend to use the plane in. Some of them are just absolute, you got to do them, okay? Others depend on the type of use. All right, so Aviate, you should really put annual here as well as airworthiness directives. So annual inspection as well as airworthiness directives. So every airplane that's Part 93, we're talking about Part 93 here in the FARs, Part 91. Part 91 aircraft have to have an annual inspection. So every 12 calendar months, we need to take all the inspection panels off, take the cowling off, just do do a big inspection on the airplane and fix things that don't meet spec. That has to get done annually. And at the same time, we're looking at any airworthiness directives that apply. What's an airworthiness directive? That is a directive that comes from the FAA. And it basically says you must do something about this, whatever that is. That's an airworthiness, and it's directive. You got to do it. You ever get a recall for your car from Ford or Chevy or anybody? You get a recall? What do you typically do with it? I typically just throw it away. Depending on what it says, I usually throw it away. But it depends on what it says, right? So think about an airworthiness directive kind of like that, except it doesn't come from the manufacturer, it comes from the FAA. Okay? And you are required to comply. You don't have a choice. You got to comply with it. That may not mean you have to do anything other than inspect it and everything is okay, and you put an entry in the logbook that says, I inspected, I complied with this airworthiness directive via doing this, or it doesn't apply because the serial number isn't within the range, or whatever the case may be. But you have to do something with it, and it has to be recorded in the logbook, as does the annual inspection. Okay. The V is a VOR check. Okay, a VOR check needs to be done every 30 days. This only applies if you're flying IFR. If you're not flying IFR, you don't have to do a VOR check. So you don't have to have a valid VOR check on the airplane every 30 days unless you're flying VOR. Okay? I changed this up a little bit. The I for inspections here, make this 100 hour. 100 hour inspection. Okay. The 100 hour inspection is an inspection that's done if you're using the airplane for, if you're renting your airplane out, you're using it for training. It's not just your own personal use. So all of my planes that I have in the school have to undergo a 100-hour inspection. So that means every 100 TAC hours, I have to take that plane down and essentially do another annual. So every 12 calendar months, I have to do an annual, but also every 100 hours of flight time, I have to do an annual on the airplane. So 100 hour, you need to do if the airplane's used for hire or for rental or something like that. Under Part 91, we're not talking about commercial charter operations. That's Part 135. They have their own set of rules. We're talking about general aviation, Part 91. Okay, so consider that 100 hour. A, altimeter and pitot-static system. IFR only. So the altimeter, the altimeter needs to be, the altimeter you need to get done every 24 calendar months. Excuse me, no, the altimeter and pitot-static system, IFR only. Yeah, IFR only. If you're not flying IFR, you never have to have this checked. Transponder, only if you're flying in airspace that requires a transponder. And both of these are every 24 calendar months. So every 24 calendar months, the altimeter / pitot-static system and the transponder need to be tested and inspected every 24 calendar months. And then the last one is the ELT, and this is done annually, every 12 calendar months. Typically it's done with the annual, but it doesn't have to be. It just has to be within a 12 calendar month period. Those are the inspections that you need to find in the aircraft logbook. So every airplane has a set of logbooks, maintenance logbooks. That's where this stuff, that's where these inspections and stuff are logged. Okay? And if you guys haven't seen the logbooks for the airplanes that you're flying here, I encourage you to ask your instructor, show me the aircraft logs. They're on the shelf in there. Look at the logs. You'll see all these things. Or you'll see the ones that apply to us. Okay? The other thing I'll say about aircraft logs is if you ever go rent a plane or you go fly a plane from someplace, you're renting the plane, even ours. Who's responsible to make sure that the annual and the transponder or ELT got tested and inspected? Am I responsible?
Owner of the plane.
Huh?
Owner of the plane.
And you.
Piloting.
And you. And you. All right, so I'm going to go back to 91.7 here. There you go. The pilot in command is responsible for determining whether that aircraft is in condition for safe. The pilot in command shall get right. Part of being responsible for it being in a condition for safe flight is to make sure that it is in a continued airworthiness condition. It's your responsibility. All right. So that's inspections. Annually, 30 days, 100 hour, 24 calendar months, altimeter transponder. ELT is every year. The ELT is emergency locator transmitter. There is an exception when when you can fly an airplane under Part 91 that doesn't have an operating and tested and inspected ELT. That's if the airplane is used. This is a kind of an esoteric question. You might get on a written test. You could get it on a written test. If an examiner asks you this and you get it wrong, you're going to fail over this, okay? But an ELT, if it's in a flight school airplane, okay, and you take the ELT out because it needs to be worked on or something, you can make an entry in the logbook that it doesn't have an ELT, but you can't fly more than 50 miles from the airport. You got to stay within 50 miles. And then once it's fixed, you put it back in. But that's kind of a weird thing, but it's legal. All right, so we've got documents, we've got inspection, and the last one is equipment. There's certain equipment that needs to be operational on the airplane. Okay? And there's a number of acronyms for this. Tomato flames during the day VFR. Night VFR would be tomato flames plus flaps. Day or night IFR would be tomato flames plus flaps plus grab card. Right? And all these things list equipment that that needs to be operational based on the kind of operation. So day VFR is a kind of operation. Night VFR is a different kind of operation. IFR, day or night, is a different kind of operations. Okay? So you can memorize all of these to what they mean, but for me, it's just easier to remember this. 91.205. If you go to 91.205, there's your list by kinds of operation. Day VFR, night VFR, IFR. And it just lists everything. It's easier for me to do that. All right, so there's if you comply with these things before you fly, whether you own the airplane or you're renting the airplane, it is your responsibility to make sure that airplane is in an airworthy condition. How do you make sure an airplane is in an airworthy condition? The acronym is DIE. Documents have to be on board the airplane. Inspections have to have been done, and the equipment that's necessary for that kind of operation has to be operating on the airplane. If you meet these three things, you have an airworthy airplane. I hear a lot of people say, well, I do a pre-flight inspection. Yeah, you do. That's good. You should do a pre-flight inspection. That's absolutely true. But part of that pre-flight action that you're doing is this. You want to make sure these things, if these are in play and everything's working, everything's good, you have an airworthy airplane. Okay? All right. Any questions? I didn't think I'd get through that. I got through it. I rushed it a little bit, but all right. So I got 5 minutes, so I'm going to ask you some questions. Put your notes away. Close your books. Let's see. What are the 6 flight instruments?
Altimeter, airspeed indicator, attitude indicator, vertical speed indicator, heading indicator, turn indicator.
Okay. 1, 2, 3, 4, 5, 6. Which ones are pedostatic?
Altimeter? Yeah, that's it. Airspeed indicator.
Okay. Which leaves gyroscopic. Of the gyroscopic instruments, which ones are typically vacuum driven? Okay. Good. All right. That's good. Okay. Good. And what does a turn coordinator give you? Gives you 2 kinds of information. What does it give you?
Whether or not if you're sinking or skidding.
Okay, so quality of turn, and well, it gives you the direction, but it also gives you something else. It gives you rate and quality. Can give you rate and quality if you hold it in the right place. Okay. What are the different types of altitude?
True altitude.
And what is that?
True altitude.
Yeah, what is that? Altitude above what? Sea level. What's another altitude? Absolute altitude. So sometimes we refer this as MSL and HEL, main sea level or above ground level. What's another one?
Indicated altitude.
Indicated altitude. What's that?
What's being shown.
We're talking about altitude.
Pressure.
Pressure altitude. Okay. Let's do it this way. Pressure, altitude, density, altitude. What are those? What's pressure, altitude?
How higher you are above 29 point.
Great. Height above the standard datum plane. What's density, altitude?
Pressure, altitude, calibrated, or calculated for temperature and pressure.
Temperature and pressure, right. So it's PA adjusted for non-standard pressure and temperature. So when we start talking about changes, anything atmospheric related, so much, and I told you this before, whenever we talk about flying, I can hardly get through one of these 15 classes without the atmosphere coming up, with atmospheric stuff coming up, because we're flying in the atmosphere. And there's two things that I'm constantly talking about when I talk about atmosphere. What are those two things? Pressure and temperature. So whenever we make adjustments to things like altitude or airspeed, we're adjusting for pressure and temperature. Those are the things we're adjusting for. That changes everything. Okay. All right, airspeed. What are my airspeeds? True airspeed, calibrated airspeed, indicated airspeed, ground speed. What's true? What's indicated airspeed? What you read. What's calibrated airspeed?
It's just indicated.
Calibrate for position.
Installation errors.
Installation and position error. But you start with this. So calibrated is indicated, corrected for something. True airspeed is going to be calibrated, corrected for something, and ground speed is going to be true airspeed, corrected for something, right? So calibrated is indicated, corrected for position, and instrument error. That's calibrated. True airspeed is calibrated airspeed, corrected for pressure and temperature. Pressure and temp. And ground speed is true airspeed corrected. It's true airspeed corrected for wind. That's our airspeeds right there. Okay. All right, guys. Next week, I believe is weight and balance, if I'm not mistaken. Yeah, next week is weight and balance. So weight and balance. So in your bind. So there's a chapter in the book to read. In your binders, under tab 8, I believe. Yeah, tab 8 is a weight and balance tab. There is also printed information out of the weight and balance handbook. Okay, so there's a few pages in there that comes direct, so that you didn't have to buy the weight and balance handbook. I put that in your binder. Read that.
What tab is it?
Tab 8. Is it tab 8? Tab 8. Okay. Read the chapter and read that tab so that you can come more informed next week before we start. Okay?
So I'm getting the pilot kit after this.
Yep.
So for the book, does it have the chapters that, or what chapter we'll have to be reading before the next?
So I will tell you, you want to read chapter, well, in your binder that you're going to get, read the stuff under tab 8, and in the POH in the PHAC read chapter 10.
Okay.
Okay, guys. See you next week.